So good morning, everyone. My name is Dr. Matthew Ray, and I'm delighted to welcome you to the second FRCPath masterclass. So we've obviously, again, got a fantastic lineup of speakers for you, and we're going to get started. So first of all, I'd like to introduce Professor Kareem Miran, who's one of the professors in endocrinology and diabetes here at Imperial. And he's going to give us a talk on T3, what's the evidence of an update in T3.
Great, I've got my microphone on. Okay, so if you've got any questions when we go, just feel free to put your hand up if you're in the room. Zoom is a bit more tricky because, I can maybe see your hand over here. Yeah, like that. We're recording. Okay, so T3, life-ironing, is the hormone which is active and binds to receptors peripherally and makes your beta receptors, adrenal receptors, more sensitive, which is why patients with hyperthyroidism present with features of having too much adrenaline, like tachycardia and palpitations and so on. And it also, of course, increases your basal metabolic rate. So it's a perfect drug of abuse if you want to lose weight and take excess of it. And it's difficult to argue with patients when they say they feel good on it. And you've got to remind them about the side effects, which are osteoporosis, which is a real problem, and in some cases arrhythmia, because patients with T3 toxicosis sometimes present with atrial fibrillation. And so really the question is, what is the safe thing to do? And the way to handle this is look for evidence. And what you discover is that there isn't any real genuine evidence for the use of life-ironing. Okay? Let's move forward here. So I'm also going to go through a very recent publication in European Journal of Endocrinology, December last year. And essentially, they have suggested that T3 is not effective. What is interesting is that there's a lot of non-blind studies that suggest that that T3 is helpful. Let me just check here, comment here in the chat. Let me just adjust the volume in this room. Shall I just turn the microphone off in the room, or is this microphone helpful? Yeah? I don't know if it's interrupting the Zoom a lot. I'm just thinking if I can adjust the volume somehow. Just give me a second. Yeah, anything I can. Okay. Let's see if that's any better. Is it the same? Okay. Yeah, so non-blind studies suggest that T3 is magic, okay? And blind studies look to me like there's a very potent placebo effect. So this is the study that is most recent, okay? A randomized double-blind placebo-controlled trial, that's what you want, on T4 and T3 combination therapy in totally thyroidized subjects, okay? And the question is, does a T3 help? And this is the problem, right? There's lots and lots of websites that say that I have a problem, like free T3 is at risk. And they're also published in the journals. So if you don't get emails and say, please could you send your paper to my journal, because we'd be very keen to publish it. So that's what these journals are, right? They look like they're real, but you'll find that it's experimental clinical diabetes, which actually is not a high impact journal, okay? And so there's a lot of this, and it's quite easy to publish, case reports, or I felt tired and then took T3 and felt better. It's that kind of level of evidence, but they quote them in kind of publications here, symptomatic relief, okay, when people have optimum T3 levels. And then there's books like this, Stop the Thyroid Madness, and this is quite an interesting book, okay? And the opening line is, the problem is your doctor, okay? That is the problem that you have if you need T3, that they won't give it to you, okay? And then they say, in this book, it says, doctors only present an hour in their medical course learning about the thyroid. And there is a lecture that's probably 1 hour long in the curriculum. And the other thing is to say doctors don't know any better because they don't feel the symptoms that you feel. And it is a shame that we need to fight to get what our bodies need. Because I know I need it, when I take it, I feel better. Okay? And you have patients, I have patients like this, And they come along and say, I know it works, doctor, because when I take my T3, I can feel my thyroid gland tingling. Okay, it's that kind of level of evidence. The other problem is that in the UK, we've got very weak guidelines. Okay, so the Americans and Europeans, like the ATA and the ETA, they say quite clearly that T4 is the choice in hypothyroidism, and it does not support the combined use due to insufficient evidence from controlled trials and lack of long-term T3 safety data. Okay, and also the unidentified T formulations that mirror natural physiology. Okay, and the problem, of course, is that when you take thyroxine, T4, it is converted by duodenators to T3 as you need it in the tissues that need it. Okay, whereas if you take T3, there's no auto-local regulation. The British Thyroid Association are much more wishy-washy. They say the combination of therapy in patient hypothyroidism should not be used routinely, but consider an experimental approach if persistent complaints despite TSH in the reference range. And you have an open and balanced discussion of benefits, likely risks of over-replacement. And the problem that this completely misses is the placebo effect. Because if you say to people, let's see if you feel better when you take this tablet, they will, and they'll expect to feel better if you give them a tablet when they're feeling particularly tired. Okay, anything will regress back to the mean. And so it's a problem. So this is the study, okay? They were going to compare the combination therapy, and they looked at an objective biochemical marker, SHBG, in patients with no thyroid glands, with no chance of any endogenous function. And they basically randomized them to two different doses, okay? One with T4 and one with some replacement T3. It was quite cleverly done to make sure it was properly blinded, okay? And they looked at quality of life. And then they looked at these genes, deodorinase RS225014 and MCP10RS blah, blah, blah. Why are we looking at these weird genes? Okay, this is in this year's European Endocrine Journal. So let me just rewind a few years and explain what this genetic craziness is. Okay, it's quite a fascinating story. So if you go back quite a long time in 2005, there was a very, very good study, the Western Area T4-T3 study, in 2005, and they did it properly, and they took almost 700 people who were stable on thyroxine, and they said, we're going to cut your dose by 50 micrograms, but if you're on 100, we'll give you 50, and we'll give you a capsule that either contains a replacement 50 or some T3 instead, okay? And we'll do it blind. So you'll be either on the same thyroxine as you were on before, or you'll be on T4 and a bit of T3, which is equivalent. And then we'll see how tired you are on this new combination. And they did this GHQ, General Health Questionnaire score, all right? And it scores you 0 to 36. There's 12 questions, each scored 0 to 3, okay? And if you're fantastically happy and positive, you get 0. And if you're really tired, you get 36, okay? That's the range of how it works. And just to summarize what they found, the tiredness score out of 36 in most people is 13.5 if they're on when they start the trial. Whenever you go into a trial, you feel better. They would drop their tiredness score 3 months later from 13.5 to 11.5 in both groups. Okay, the T4 and the T3 groups both felt better. So there's a fabulous placebo effect. Okay, and it persisted for a year. So they felt better, but half of them were on the same tablets as before. So this is good evidence that this is a placebo effect. And they quoted here, note the persistent placebo effect. Okay, so that is, in my view, the end of the story. We've got clear data that shows that T3 is not better than T4, so we should just use T4. It's easier to control, got a nice long half-life, very stable, and you don't need to keep changing the dose all the time. T3, short half-life, it wears off in the morning if you take it, you might feel tired in the afternoon, plus all the psychology that goes with it. So here's their outcome, 2005. Okay, they were very clear. Do not provide conclusive evidence of benefit from partial of the T4 by T3. They also emphasized a large and sustained placebo effect. Okay, very clear. At that time, T3 cost £4 a month and T4 cost £1 a month. Okay, so in a cash-strapped economy, you want to use the most efficient, and so basically there's good data here that says we should be using T4. All happy with that? Yeah? Quite clear. Okay. And then another meta-analysis of that study plus loads of others said the same thing. There's no benefit of using T. This is 2006 now, a year later. Okay, so we've got plenty of evidence or that there's no difference. Okay, and then the price of T3 started going up. Okay, and this is a UK problem only. It happened with hydrocortisone and with T3, and it simply happened because one player, one company, started bribing other companies to not make it, and they just upped the price and upped the price and upped the price to £240 a month, right? So now there's a huge push to not use T3. Now there were a lot of people around the country who basically were given T3 because it was £4, not £1, but they said they felt better, and a lot of doctors just let it go because it's a slight excess. The patient says, I feel happy on this, they don't want to mess with it. Maybe it's placebo, they didn't care, right? But when it became £200 a month, right, it was coming out of their budgets. And suddenly there's a big push from the NHS saying, do not prescribe T3, do not start T3 unless there's some good reason to do so. Now, the only reason that I use T3 is in patients who have had thyroid cancer and who have had a total thyroidectomy. And in order to suppress the TSH for 8 weeks only, you need a short course of T3. Okay, that's its only use. And you do that in order to do uptake scans, just for diagnostic purposes, for no other reason. And then when you prove they've got no recurrent cancer, you just put them back on T4. That's what it's licensed for and meant to be used for. But type people use it because they feel better on it. But this caused a lot of problems, okay? And various guidelines came out saying we should stop doing this, okay? Meanwhile, thyroxine remained at £1.50 a month. So there's the position statement that came out just before lockdown. Prescribers should not initiate T3. So, of course, a lot of private clinics were prescribing T3, okay? And they said GPs should not take on prescribed patients initiated in T3 in private clinics abroad or via other self-funded routes. So basically what happened, patients would say, I feel tired and would buy T3 from usually Turkey, and then they'd come back to the UK and say, can you, I'm being prescribed this drug by my specialist in Turkey, brackets private, can you continue it at £240 a month, okay? And the answer is no, because there's no evidence of benefit. And so I had to give the talk to a lot of people because there's a huge push, and there's lots of little websites that say, don't believe your GP, or don't believe your, you know, the entity saving money, our health matters, we paid our taxes, we should get this expensive T3. And because it's expensive, it's an even better placebo, okay? Because that's how placebos work. Okay, so then this came out, right? This is the background, right? And so 2 years after I thought that study conclusively proved that T3 was a placebo, right? They reanalyzed the data of that study that showed a good placebo effect, okay? Similar authors, but a few other now famous geneticists. And they said, it might be that if you've got a variable deadenase gene, that you might not convert T4 to T3 properly. And so they did the big mistake of all time, which is to sequence loads of SNPs, okay? And then look to see if there's any variability. So here's a load of, these are the enzymes, the deadenases, in the periphery of all your cells that convert T4 to T3. And these are single point mutations, okay? They're not mutations, they're single point variability, let's call them, okay? And so, for example, for each of these, there are different wild types, okay? And there's common ones and there's less common ones. And they don't, I don't think, have any impact on the function of that gene or the protein. But if you look at them, right, for example, this particular variant, okay, they measured things like the T3-T4 ratio, okay, and they said, if you have this allele, TT alleles, there were 399 of the 600 patients had that allele, okay, their T3-T4 ratio was 0.187. On the other hand, if you take the homozygous for the other point mutation, let's call it, okay, there were only 16 of those, pretty similar. So they said this SNP, no difference, and therefore we'll ignore it. And they did lots of them, and then they say, oh, look, now this one here has got a different T4-T ratio compared to this, and therefore there's a trend, okay, which is significant. And this is basically a lot of nonsense, but there's 1 point change in the sequence of this gene in this particular SNP, which is numbered that they're trying to suggest might be associated with lack of function because the T4 ratio in that study was not the same. And so they reanalyzed that data, and then a year later they published another set of genes. Okay, they looked at this tiredness score that I showed you earlier, and they reanalyzed it. So this is the same thing, the same different mutations again, but this time they looked at the tiredness score. Okay, so this tiredness score here, remember, it goes from 13.5 to 11. So they plot the tiredness scores of these groups. So they said 399 patients with this allele, their tiredness score 13.4. This had this allele 13.5, and this is not significant. But if you do enough of them, by chance alone, you find what they're going to call a trend in tiredness. So this group had a tiredness score of 12.8. The heterozygote had 13.6. The homozygotes had a 14.1. They call that a trend. Okay, so there's no trend there, but there is a trend here, and it's significant. And so when you look at this curve and reanalyze it by splitting them between the different alleles, you have 3 different graphs. This is what you see. So the TT group, okay, they say here's a tiredness trend, okay? The tiredness increases as you go from this gene to this gene, and it's significant. So what does that mean? If you read the little rubric down here, I'll just enlarge it, right? It says, this is in the paper, they published a thing saying, maybe there is a gene effect and maybe that will happen. So they point out no correction was made for multiple testing because despite being the largest study to date, it is still underpowered to detect all but very large differential gene effects. Instead, we have chosen to report the p-value and associations which should be considered suggestive and have qualified our findings very clearly that we to replicate this as a type, there's a risk of a type 1 error. In other words, if you measure things lots of times, you're going to find a difference by chance alone. That's what's happened. Okay, this is a type 1 error, and they're saying it might be a type 1 error. Someone needs to repeat this. But that's not what happens, okay? So even the abstract says our results require replication, okay? But they have published this and they've said maybe this particular polymorphism might mean that you'll be tired with normal thyroid function tests, okay? P equals 0.03. So websites go nuts, okay? So despite it saying this is probably not real, the websites say it's definitely real, okay? Don't believe your doctor. To explain this patient briefly, this enzyme, the researchers found that a tiny change in this gene could mean that while the body gets enough T3, the brain doesn't. What a great summary, okay? So of course this went viral all over the place, all these websites saying, this is good evidence now. There's a big study and a big group and a good journal that says we must all have T3. No question about repeating it or type 1 errors or anything, okay? And so a number of different papers have been published, all saying it doesn't work like this, and yet patients are going to keep on insisting that they have T3. So let me show you what the actual study was, okay? It's a longitudinal, prospective, double-blind, basically properly done study for 3 years, and they basically did something similar. They gave them drops of T3 or T4 added back to their thyroid replacement. And they basically randomized it completely fairly, so that there were patients in both groups who went through everything, okay? And there are some dropouts as you'd expect. And they used an intention to treat analysis to make sure that they had a group had T4 and placebo and a group T4 and T3. Okay, and it was a good study. 121 patients basically attended all the appointments. And to summarize the outcome, there was no difference in tissue markers. SHBG was slightly higher in the T3 group. So they were slightly biochemically hyperthyroid compared to placebo, okay? Which is what they wanted. They wanted to slightly over-replacement because the patient said, all the old studies that show no difference, they didn't give enough T3. We need to be slightly toxic in order to feel the benefit. So if you look at the actual data, right? So this is the baseline data, the TS 1.4 and 1.1, okay? The placebo group had a TSH of 2.6 by the end because they were missing the T3, okay? It's still normal in the reference range, but essentially the group who got T3 were given a little bit more, okay? So the T6 went up on the placebo, but not on T4 and T3. So you might expect from that they'll feel better, okay? Secondly, they were generous in the same way with the T3. The T went down a bit in the placebo and up on those on the combination. So there's the T3 going from 3 to 3.2 and 3 to 2.9. So it's not outside the reference range, but it's significantly different. So they are actually slightly better replaced with T3. Okay, but they didn't know what they were on, and they did all the tiredness questionnaires. And they found no difference in any bone turnover. So this is the dose they're giving is safe. It's not causing osteoporosis. Okay, and basically they did have a slightly higher T3 ratio, so they're giving them a little bit more T3 than the placebo group. Okay, and the outcome of this very, very good study is there was no difference in the scores that matter to people, tiredness score. Okay, and so this is very good data now because it does what the patients asked, which is they said, we don't want to do these studies that are just blind. We want to actually slightly over-replace and blinded, okay? And they found no correlations in anything to summarize them. Okay, so for some hypothyroid symptoms, no difference between the groups baseline and at the end, okay? They all got slightly better, as we always know by the study. Tiredness, no difference, okay? In fact, whatever you looked at, there was no difference, okay? And they did lots of tiredness scores. So there's no difference in anything. So I think you can be fairly clear now that giving T3 is not helpful. And the most frequent adverse effect was TSH reduction because some patients were being overpaid and they started to lower TSH, but it was still kept within the reference range in most patients. So then they asked them what they preferred, and 56% preferred the combination and 60% preferred the placebo because they didn't know what they were on. So that was clearly not significant. And then in the same study, they also took the same genes, and they also found that in this study, when it was repeated, they didn't find any effect of those genes on it. So in summary, the combination of T3 and T4 against placebo is not helpful. And if you take T3, you get a significant rise in T3, and there's no change in this study in any markers of quality of life, tiredness, or weight loss. Because the only way that it helps you to lose weight is if you deliberately take too much and have a suppressed TSH. But if you're properly replaced, it doesn't give you the benefits that people want. And if you over-replace yourself with any thyroxine or T3, you're going to get osteoporosis and AF. So there's the conclusion, okay? Basically, the combination of the dose adapted according to TSH level twice daily T3 is capable to restore normal blood levels, but there's no benefit to doing so in any marker or any symptoms. And it doesn't help you whatever genes you have either. So the first thing we need to do is update our guidelines, because our guidelines need to be the same as the American and the European, which basically should say that T4 is the gene of choice, and T3 experimental approaches give you a profound placebo effect. So I've set up a T3 withdrawal clinic, right? And I've done this because the CCGs locally were saying, can we please get someone to get people off T3 from their private clinics? Because if the patient arrives on T3, you can't just stop it, okay? And so the patients insist that someone sort it out. So I've done this kind of, and it's labeled quite clearly on their letter, this is a T3 withdrawal clinic. And what I found is quite surprising. Okay, first of all, they're usually on full replacement, and the dose of T3 is very variable. Some patients on 2.5 micrograms once or twice daily, which would result in normal function. But there are some on 40 micrograms 3 times a day who are properly toxic. Okay, and they love it, and they're nice and thin, but they've got osteoporosis and other things. They also are on these things, okay? Armathyroid is so-called natural thyroxine. And if you look into it, it's actually desiccated porcine thyroxine. And what they did, they go around the abattoirs and collect all the pigs' thyroid glands and mash them up and make little capsules that they sell to you called armathyroid. And it's natural because it's not man-made, but it's not very well regulated. But it's very popular around the world. And then you find that also on the other things, ashwagandha, these are all new things to me, turmeric, which you've all heard of, and coenzyme Q. If you look up coenzyme Q, you'll remember that this is on the electron transport pathway in the mitochondria. So I don't know how they have this capsule that contains what they say is coenzyme Q. Now, if you take an enzyme by mouthful, it'll be digested. So the thing is, these are people who are, I think, quite vulnerable, and they're on lots of replacements, and they use T3, and they're also on these other things because they feel tired. And when you got them off the T3, you then discover that they probably don't even need a T4. And you go back to their original, their very first prescription of thyroxine, and it's done with TSH is 4. So if you look back, these are patients who are really tired with normal TFTs, and they said to the GP, look, I know I've got it. I've read the book, I'm putting on weight, I'm feeling tired. I looked at this picture. You see this picture of this person who's got myxedema? That's me. Let me just try it. A trial of therapy. And they go on thyroxine, 50 micrograms, and they go, this is amazing. I feel so much better. And then about a month later, it wears off, and then they increase the dose. But by that point, they're established on thyroxine, and no one dare stop it. And they've got it for years and years and years. But actually, underneath it, they've got a normal thyroid, and it's suppressed because they're on thyroxine, and the TSH is undetectable because they take too much. And this is a really common story, okay? So you get this sort of stuff, okay? Clean ashwagandha, future turmeric, and high-strength coenzyme Q from Boots, okay? And in November 22, there's a special offer, £38 for this placebo, okay? I mean, it's got expensive to work. So I think we've got to think about protecting these people because they are on very expensive placebos, but also expensive teeth which they try to get from the NHS because it's very expensive, but also it doesn't work and it's going to have side effects of doses that they want. And I think an important point is if we spend resources on unproven treatments, then somebody else is not going to get something that the NHS can actually benefit people. So basically, the placebo effect is important, okay, and that's something that we should think about. And I'll just tell you a bit about what I think happens here. Okay, this is what the BTA has said we should do: trial of therapy. And trial of therapy is a terrible thing because what happens is here's my well-being score against time. This might be months, weeks, days, hours, whatever. But we've all got good and bad days, good and bad weeks, right? And what happens to these very tired people is when they're really, really tired, they go and pay private service. I need to see a specialist because I can't cope with it, okay? And whatever that specialist gives them, placebo or otherwise, will work because they're so at such a low end that wherever they do, they're better. And they go, you know, that private doctor's amazing. He gave me this stuff called coenzyme Q, and it's really working so much better. Vitamin D will do the same probably, right? And then it wears off, and they say, oh, I'm getting tired again. So they're going to see their private specialist again, and he says, double the dose, okay? And they double the dose and they feel better again. And that's the problem with childhood therapy in that it makes people think that this gene is active. And despite my saying this doesn't work, the tiredness and depression that a lot of us have make us vulnerable to being manipulated by websites and like that. So just avoid that carefully. Now, the other problem I have, right, is when I see the patients, okay, if they are very tired on T3, they refuse. They say, listen, doctor, I can't come off it. I'm so tired. I must keep going, right? I'm really tired, so I can't stop it. I'm going to wait till something better, okay, and then I might. Okay, so when they're up here, they go, all right, then, I'm feeling okay now. I'm going to stop the T3. And of course, that will be associated with a worsening of how tired they are. So I knew it, doctor. I stopped the T3 as you told me to, and I'm feeling more tired. Okay, and that's because they should have stopped it here, at which point they would have felt better. But this kind of hidden placebo in reverse also makes life very tricky for people who believe something. The other problem is a lot of us have got chronic fatigue and brain fog. This is a normal thing, feeling tired. And quite a lot of patients who are on T3 have had lots of trauma in the past and need other therapies rather than these expensive placebos that don't work. Now, I don't think the placebo is a bad thing, but if you're paying for treatment with no evidence of benefit on top of it, I think that's wrong. Look at the history and try and get people off thyroxine if they had a child of thyroxine, because They don't have they've got a normal underlying thyroid gland underneath. Okay, and even when on these treatments, they are really afraid to release any of them. The other thing to do is to explain to people that having suppressed TSH is not a good thing. These websites say, I know lots of patients with no TSH, they feel absolutely fine, okay? And so, and there's people who go online and they say, look, your doctor will tell you that suppressed TSH is bad, okay? But don't believe them because I've got no TSH and I know that I'm fine. And one of the patients who I'm trying to get off T3, he had a TSH of 1 before he started. He was definitely normal. And he said, what that proves is the biochemists are useless. It proves that biochemistry does not work, and I know I've got it. And I said, how do you know you've got it? He said, well, when I don't take my thyroxine, I feel terrible. When I take it, I feel better. And I said, but that's not, that's how you can say, no, do you know what? You know my phone, right? My phone can detect my fingerprint. If I'm not on thyroxine, it won't recognize me. Okay? That proves beyond doubt that I need thyroxine to have my phone detect my fingerprint because my phone doesn't know if I'm thyroxine or not. That's a good control, he said. Anyway, what we need is to find some other placebo, and there are cheaper placebos. A lot of people get selenium. Where did you get this from? Holland & Barrett. Now, Holland & Barrett is a shop where nothing works, okay? It's entirely full of placebos of every sort, okay? And there's no active ingredient in any drug there except vitamin D, and that's the only thing that they actually have. And this is the sort of thing that you can get if you look online for selenium. All of these things would come to a die. I mean, you get selenium from Brazil nuts, so a good cheap source of selenium. If you think you need it, is Brazil nuts. It's much cheaper than their Holland & Barrett. Even Holland & Barrett now sell Brazil nuts as well. Anyway, get Tesco's or Sainsbury's own because that's a lot cheaper. And so, do you know, I've started saying to people, get some Brazil nuts and take one a day into your teeth and go, doctor, you know what? It works. And I know it's a total placebo, and I'm becoming guilty of colluding with them to use placebos. But I realize that they need some kind of crutch, because if you don't do that, they just feel tired and don't follow your advice. And that also has them, okay, just for equality. Now, there's lots of, this is not the first time that people have shown no benefit, okay? There's quite a lot of authors over the years that have also said, this is looking at comparative of T4, desiccated, this is the armored thyroid from pigs I told you about, and then the combination. And they did a very similar study, randomized them into 3 groups, and basically showed that basically there's no difference. Okay, so 75 patients had all treatments in random order 22 weeks each. That's T4 alone, T4 and T3, or desiccated thyroid extract. Okay, and they cropped them over and cropped them over. Everyone got everything. And basically summarize, okay, all of these questionnaires for tiredness, no difference. Okay, so I think we're quite clear that T4, the combination, or desiccated thyroid extract, don't give you any benefit, okay? And that's despite the fact that you're making them slightly toxic. So all these values are highly significant. That is, the levels, when you give them these substances, you're making them truly hyperthyroid, and it doesn't work, okay? And then in that study, they also analyzed the genes and also found no effect of those 3 gene types. So I'm pretty confident now that the whole thing is all made up. I've done that already. So this is my protocol to get people off drugs, because what I realize is if you take any hormone, and that applies to cortisone, thyroxine, if you take thyroxine for long enough, you will have a fully suppressed TSH, and you have therefore an atrophic thyroid gland. So if you stop it, you will go under. You will actually become hypothyroid for a bit. And if you do that, the patients will feel it and say, I can't do this. Okay, and secondly, if you do stop it, it takes a long time because first of all, the pituitary's got to recover and start making TSH. That can take 2 months. They have tiredness with no TSH for 2 months. The T4 drops and drops and drops. Then the TSH start to come up, and then after another interval, the thyroxine levels start coming up. So there's a long period of feeling absolutely knackered that is genuine, and therefore you've got to really slowly. So this is a protocol a patient taught me, right? So what you do is this patient's on 6, they need 0, okay, but they're on 60 micrograms of this desiccated stuff. So what you do is you say, stay on that, and on Thursday, you take half the dose, which will give your kit a bit of a kick. And before you go under, you go back to full dose. And then next week, you do it on Tuesday and Friday. The following week, you do it on Tuesday, Thursday, and Saturday. You slowly do that. And of course, some patients want monitoring. So I do a TSH, T4, and T3 every 7 weeks to prove to them that there is some recovery. And if you do that and it needs a lot of hand holding, you can get them off these drugs. But this is the kind of protocol that it's nice and colourful, maybe not a placebo, but it makes people want to try and see. So, last of all, this is a journal, Frontiers, that has dropped in quality from being quite a good journal to absolutely dreadful, and they will take absolutely anything. So if you want to publish something that you can't publish and it's completely useless, Frontiers in Endocrinology is your journal, okay? So here's an example of the kind of craziness, right? So they published this quite recently, effective T3 on quality of life in female hypothyroid patients with symptoms of tiredness, basically. A randomized crossover study, not blind. Okay, at what point you're not a blind study in a tiredness study? It's completely crazy. So it's a fatigue questionnaire in this population, and they're on T4 once a day or T3 thrice a day. Okay, and of course it worked. Okay, so their physical fatigue score baseline was 12, and there's no difference between them. But by the time they went on to T3 for a bit, highly significant improvements in physical, mental, and total fatigue, whatever that means, okay? So this is a profound placebo effect, okay? And if you read their paper, they also analyzed the gene and found no effect. In fact, paradoxically, the only significant difference we found between the presence of this gene, okay, was a lower score in the overall quality of life on T4 treatment. Improved quality of life. Okay, this result is in contrast to the hypothesis that this polymorphism may impair the effect of the arginine. So this, because it was an open label trial, they just had a placebo effect, and by chance, it showed the opposite effect of this other genetic study. So these non-blind studies are very misleading. You need to really ignore them, okay? And the problem is now these journals will publish anything, okay? And there's more and more of them. So you have to be very, very circumspect when you read them, because if you read the abstract, it tells you that these things are good. Anyway, in my summary, there's no evidence benefit of T3 over T4. There's a very profound placebo effect. Money spent on T3 could be spent on something else, because every time a prescription for T3 is written, somebody else has to have a wage freeze, okay? And the other thing is, volunteers are being taken advantage of. And trials of therapy are flawed. We should stop doing them. With new slow weaning of hormones, if patients are put on high dosing for long periods in order to get them off it. Okay, I think that's all. Thank you very much. Any questions about that or thoughts? Okay, so we measure SHBG, there's a question on the chat, because it's a marker of being over-replaced. So when you make people hyperthyroid, their SHBG goes up. It's a bit like estrogen. So what they used there as something that was a non-thyroid marker of being over-replaced. Any other questions or worries?
Do you think that there's more that we can do in the NHS to try and stop sort of private healthcare providers sort of encouraging these things?
It's very hard, isn't it? Because I've spoken to patients who eventually have come off it, and what they say is when they go to a private provider, and there are private laboratories that run all kinds of weird assays, including reverse T3, that's very popular. That make people say, oh, look, the reverse T3 proves that I need T3, right? Because it mops up the T3. They make up stuff, right? But they also say that the private providers say, oh, they don't. The NHS is trying to save money, so they're not going to give you the best treatment. You know, they're going to save money. If you want to have good treatment, you come to us. And of course, that's quite believable, really. The real problem.
Anyone else have any other questions?
Thank you not.
Perfect.
I'll hand over.
Perfect. Thank you very much.
Okay, thank you. I'll leave that. Thank you.
And so our next speaker is Dr. Edmund Wilkes, Dr. Ed Wilkes, who's one of the consultant clinical scientists here at Imperial, and he's going to do the next talk on mass spec.
Surgery.
So thanks for the invite, Matt. I know some people in this audience who probably know more about mass spectrometry than me now, so I hope this isn't too basic for some people. But I really wanted to go back to basics because I know that on the masters we get taught a bit about mass spectrometry, but it's quite a mystical technique still, and so I want to kind of demystify a lot of the inner workings of this, understand how it works and why it's so important. This technique is now 110 years old. It was last year, and it's probably one of the most used biased, I think it's probably one of the most important analytical methods that's actually developed through this potential. Hopefully, I'll convince you about it. But if you fall asleep now and you want to take away 4 points from this, is really to remember that mass spec is more selective than most other analytical methods, and obviously the most common one is labs, analysis. It's easily multiplexed, which is really useful and really important when we think about kind of we can measure with it in the lab. It still, however, remains a complicated technique, and anyone in here who's done it will know this. And it's a lot more complicated than quote-unquote back potential methods that we use for basic function analysis or even analysis. Really, analysis is still complicated, but and it still remains a manual technique mostly, obviously with some automation, and it's not infallible. So, despite all these facts being multiplex and selective, there are still problems with it. So again, back to basics. So this is thinking, God, when do you learn next? Maybe P stage 3 or something like that. So if you think about a structure of an atom, so sodium here, obviously it's group 1 alkaline metal, so it's got 1 electron in its outer shell. And we make that ion by just removing that electron. And it's as simple as that. So it's lost a negative charge, it becomes a positive charge. I know this is basic, but it's a really, really fundamental one of mass spectrometry. And if we were to move another electron, we would have to use this, or if we were to add an electron or something. So why is this important? So the whole idea of mass spectrometry, and lots of other methods, is that ions can be manipulated. You can do stuff with them, we can move them about. And how do we do this? Well, we obviously need to do it in a vacuum, so they're not going to bump into anything else, because obviously air is also things like alcohol, they're not doing much. But we can use magnetic fields and electric fields or electromagnetic fields to manipulate the path of ions. We can do so quickly, we can move them around. So if we have a sodium atom, and let's say we've got this tube, and I'll show you an example of literally glass tube in a second. And let's say we curved at 90 degrees and we put it in the detector here. So if we then place a strong magnetic field across this tube, so here it's showing green hole, which is the magnetic field. And the field is going kind of perpendicular to the direction of the tube. So if I was to then put a sodium atom through that somehow, it would just hit the back surface, because it's not an ion. It won't interact with that field in any way. However, if we remember our the right-hand rule for motion of ions in a magnetic field. So if you can see there, obviously the index finger is the direction of the field. I'll try to orientate it in the right way. Then the ion, if it's charged, or any charge involved ion charge, it will go perpendicular to that magnetic field. And if you think about that across the length of the tube, well, the ion is just going to go through the detector. That's mass spectrometry in a nutshell, really. So it's just manipulation of ions in a magnetic or electric field to get them through to a detector in some way, so that we can obviously detect it. So this guy, J.J. Thomson, so this was 1913 published his work, and so obviously it's the measurement of ions. And this was, I'm not sure if this was the original, but at least it was an original. And as you can see, it literally is just a metal tube bent with a vacuum cleaner to pull the air out of it. And this is one of the original, I'm not sure what you call this a mass spectrum, but this is one of the original mass spectra of neon, I think it was. So this was pioneering work, obviously looking at the isotope metals. isn't separated based on that. So in terms of the basic principles then of a mass spectrometer or a modern mass spectrometer, obviously we've got a sample at the beginning, that's what we want to measure something in. We have to ionize it in some way, told why that's so important. We have to then analyze its mass, so with a mass analyzer ethanol, so when it comes to biological molecules,
slightly just because then basically the final yeah, is that slightly, I don't know if it's knocking your that might be perfect.
how's that? We'll find out in the chat. But again, I'm just so we've got various ionizable groups in biological molecules. We all remember carboxylic acids, amines, primary, secondary, tertiary amines, and hydroxyl groups. And obviously, if we move or add an electron to it, we can make them ions. The method we use doesn't necessarily do this, but obviously it's key to remember that ions exist in nature and we can use those properties to measure them. So these three chaps won the Nobel Prize in the early 2000s or maybe the 90s for developing a method for the ionization of biological molecules. So there are some other ionization methods that you can use for, say, small molecule drugs, obviously the method we just talked about was the original work, but to do biological molecules was quite difficult until this method was invented. So this is something called electrospray ionization, and effectively all the, at least the mass specs, coupled to the liquid chromatographers in clinical labs will use this ionization method. So if you have mass specs in your lab, you could probably just go and have a look at these if you haven't already. Good. So this is a kind of simplification of how electrospray works. So if we've got our mixture of ions in our sample, which I'll talk about in a minute, if you apply a really, really high voltage, so we're talking like 3,000 volts or 300 volts, and a vacuum on the other side, let's grab So if we apply voltage, we'll start getting these small droplets forming, which contain obviously some of the iron that both cause positive and negative charges. So depending on the voltage, so it would be a negative voltage to attract positive charges. Then these droplets get smaller and smaller and smaller, and there are a few mechanisms by which then they become single charged molecules, but then in the currents ionized there. So this was a massive breakthrough, as you can imagine. That's why they were in the Nobel Prize. So these are some great animations from Prof. Jones in Warwick, and this just shows how those droplets, through Coulombic fission, split into smaller and smaller droplets until you have your ions completely desolvated, so there's no more water or whatever solvent around them. You just have those ions of whatever analyte you've got, which you can then obviously apply on mass spec and manipulate with magnetic fields. So we've talked then about ionization. So the next important bit, obviously, is how we analyze the mass of the ions we've got in that sample. So the most basic of these, and the most commonly used in lots of labs, but clinical labs especially, because they're really flexible, they're cheap, and they're relatively robust, are quadrupoles. So as the name suggests, these are quite literally just 4 poles. Modern ones actually have a slightly different shape, but most of them, it's all the same principle. And the idea is, with these 4 poles, if we apply a radio frequency voltage across these poles that alternates, I'll show you with an animation in a second, we can basically get ions to go through the center of those poles and fly through to the detector. And so if you imagine that red thing is our little ion, then obviously there's a linear in 2 dimensions from the side. But if you then flip that voltage from positive to negative across those poles, the ion will get attracted to one and then get repelled, and then get attracted and repelled. And you'll see they form this kind of wave pattern flying through the detector. And so on the left here, that blue sine wave is just how those voltages are alternating. It's not the same frequency, it's different. That's the general. And now think about that in 2 dimensions. We've got those 4 holes, and depending on the frequency at which those positive and negative voltages are flicking, we can control which ions get through and which don't. So you can see in this animation, because of the frequency of that oscillation, only the red and green ions getting through. They're the only ones that have a stable trajectory. And the blue iron is too big, so it's just basically flying out. And they literally just flying out on the inside of the detector. So this is thinking about it on the other axis, then by flicking voltages at the particular frequency of that red ion, it will go through, hit the detector, we can detect what it is, and the blue ion will just fly out the side. So if we imagine then we've got our sample being ionized through this electric spray, and if you do have a mass spectrum now, I'd really encourage you to go and have a look, because you can literally see the cone as it's formed, working by the voltage. And it's then flying into the mass spec. We've set the frequency of those colour poles to create a certain frequency, and now our red iron is getting through the colour. So the really important thing to remember about this is that this is why mass spectrometers are selected, because you can select and filter the masses that are going to be detected. So what does a mass spectrum look like? So let's say we've got this molecule. So what is this molecule? Everyone's biochemist or chemical biologist. Yeah, right? So what's this molecule? Any ideas? Even just the general kind of group of molecules this can be. Not that it's really relevant to this discussion, but you know, any ideas?
Want to say what?
Yeah, which one?
Cortisol.
Yeah, good guess. There you go. So this is cortisol. So we've ionized it. It's got a single positive charge, and that charge will be. It depends. Like it oscillates across the ions. So it depends exactly at what point you look at it. But it's, let's say it's just distributed across it. And it's got a single positive charge. So if we ionize that in our electrospray, we put it to our protocol set at a frequency that allows that mass to go through, or that mass to charge because it's an ion. We'll get a peak at the end as we detect it. So this is the molecular ion, so that's M is the kind of notation used for the molecule of interest, plus the proton, like hydrogen. So it's got a single positive charge. So our mass to charge ratio for that ion is 363.5. Let's just call it 363. And so the molecular weight of cortisol is just 1 minus that, so 363. So what are these other peaks? So this is actually quite high resolution mass spectrum. In a quadrupole, you probably wouldn't get as high resolution, so those peaks couldn't be well separated. But nevertheless, we have these 2 other peaks. So what are they? Do you know? So they're 1 mass unit more, or 1 mass charge more than the molecular. You know what they are. Again? Exactly. Yeah, so if we've got, say, let's say carbon, then at least there's a chance of one of them being a carbon 13. So the molecular ion peak will be, well, there are no carbon 13s at all, it's all normal carbon 12. And then the peak next to it, well, it's just a chance that one of those molecules has 1 carbon 13, and then the peak next to it is 2. So obviously, the bigger the molecule you have, the more abundant those peaks will be, because you've got, well, assuming you've got carbon in it, which we'll call carbon 3. So the other thing that I talked about is that mass spectrometry is easily multiplied. So why is this? So we've got our quadrupole, and we set it at a frequency that, let's say, our cortisol. So the point, the really important thing to know about mass specs, and especially quadrupoles, is that we can scan different frequencies at different times. So say at time 0, we can set the frequency to let the blue ion through. Time X, we can let the red ion through, and then the next time at high frequency, we can let the next ion through. So resolving through time, we can scan across different masses. So we can look at different things in the same mixture, assuming we actually got it in the mixture. So in this way, it's really easy, and much easier than lots of other methods, than multi-factor analysis. So I'm sure lots of you have got aspects in your labs will have, say, a steroid panel. You can measure, you've already extracted the steroids, and you can measure, say, 4, 5, 6, 7 different molecules really easily, whereas in our cells, that's very difficult. So in this way, you can just think of quadripods as mass filters, so literally just a filter letting your mass of interest through. So we talked about kind of mass spec in one dimension. So somebody heard that a long time ago now, thought, well, hang on, why don't we just put 2 mass specs on the end of each other, or do different mass spec analyses at different time points? So mass spec, tandem mass spec in space, so there are 2 separate analyzers, or tandem mass spec in time, using the same analyzer but doing something to the ion and then remeasuring. So let's say we put one protocol in the front of the analyzer. We've got ions going through from our electrode, and if we were to have a detector, we could measure that ion. So if we stuck another protocol next to it and set it to the same frequency, we just let the red ion all the way through and we could measure it again. But obviously that's really pointless because why would we want to do that? So what we can do, we do something to the ions in the middle before they get through to the next protocol. So let's say we've got our blue ion of interest, whatever it might be. We've set the ready frequency of voltages to let it through the first protocol. And if we measured at this point, we get a mass spectrum, so this is usually called like MS1. And we get a mass spectrum of that molecule of interest. So what we can do then is actually pass that anion into something called a collision cell, which is effectively another protocol. Do something to it, break it apart, or whatever, and then measure another ion that comes off the original blue ion, so in this case it's the red ion. So obviously the radio frequency voltages on this protocol will be different to the ones on this protocol. And then that way we can add even more to it. So this mass spectrum, the second one would be colloquially referred to as MS2. So what happens in this collision cell? So obviously this is an oversimplification, but this is the concept. So usually it's filled with argon. So why do we use argon? Why do we use a noble gas? It's inert, exactly. We don't want, well, in some cases you might want to do it, but in the vast majority of cases, you don't. When you put your ion through this, you don't want it to change in any way that changes its effectively. It's like it's chemical makeup. So if we put our, and you'll often see these referred to as precursor or parent ions from the first protocol into our collision cell, argon will become big, and it's just, and we give it a little tickle of energy, and we're just going to break that ion apart into its constituent atoms, effectively, or maybe obviously it has to become an iron for us to do it. So it's going to collide with this argon with a bit of voltage, and it's going to create this other ion, which you'll see referred to differently in different places as like a product or a fragment ion or a little ion. And that's obviously going to be some constituent of the original ion, and it's always going to have small mass because you knock something off. There are some collision cells, for say ICP-MS for heavy metals, that actually react the metal with certain in the collision cells and make another chemical species, but in LC-MS at least that's never the case. So let's say we've gone back to cortisol. We've got our master charge of 360 cortisol, and I'm using no decimal places because quadripods are not higher resolution, so they're not really, they need to go to 1 or 2. That's as far as they get. So we've got our parent ion, which is cortisol, ionized. We put it to our first quadripod, put it to our collision cell with all the iron in it, and it's going to break it apart. So this is just an example of a fragment ion. So you will end up getting a huge spectrum, and I'll show you the fragmentation spectrum, but you'll get a spectrum of fragment ion. So let's say this first one here, where we've lost this group on the top of the cortisol, well then this ion that remains is going to have a master charge of 267. The next one, we've knocked off this entire part of cortisol, and we're left with this small bit, and obviously it remains, the charge remains, that's why we can measure it. And that has a master charge of 121. and then say this bit breaks off and we get a master charge of 97. And some weird and wonderful rearrangement is going to happen in collision cells, so you get these kind of weird and wonderful ions, which aren't particularly stable in nature, but obviously they're stable enough in the analyzer to be able to measure them. And as you can see, all these ions will be, we'll talk about not necessarily, but specific to cortisol, because they're based on the structure of cortisol. So that's adding our next layer of selectivity. So this is the fragmentation spectrum or spectra of cortisol and penicillin. And as you can see, this is Prothnair's favourite molecule, that there's a single difference of a desaturated double bond here of penicillin. But you get different fragments because the structure is slightly different. And you can see you've got the different molecular ions here. So 363 is cortisol intact, 361 penicillin intact. And then you get some, there'll be some shared ions, so like 121 and 97, which are these common parts of it that fall off. But you'll get specific ions to the structure of the molecule, and that's how we get this selectivity. So again, just to kind of hammer it home, we've got cortisol ion at 363 applying to our first math analyzer, the first cortisol, and then there's one. We apply it on. It creates, say, this one fragment that gives it a signal, say, and we measure then that transition from 363 specifically to 121 specifically. So we're measuring that entire path, which is called the transition from 363. And the cool thing about this, which is what I'm most interested in, is that so we're talking about small molecules here, so cortisol, penicillin, other steroids, testosterone. We can measure drugs, immunosuppressants, aldosterone, angiotensin for renal activity. You can measure lots of small molecules in clinical labs, which is obviously really important to measure. But with experimentation, we can also sequence peptides. So let's say you flew, and we technically do this, I suppose, for renal activity, but let's say we've got this peptide, which has what, 14 amino acids. We ionize that in our electrospray. We put it to protocol 1, we measure its mass charge, whatever it can be, and then we fragment it. And let's say instead of just looking at one specific fragment ion, we use a different mass spectrometer to look at all of those fragment ions. And by looking at the difference and where the charge remains on those amino acids, we can sequence that peptide. And as you can imagine, that's tremendously powerful because effectively you can now do protein sequencing. And with slightly more complicated instruments, you can measure proteomes and subproteomes like phosphoproteins. So we've done the ionization, we've done the mass spec, we've done the detection, but we haven't talked about actually what happens before the mass spec, because it's not, and those of you who've been in mass spec will know that it's not as simple as like an immunoassay where you just take out all the samples, stick it in a reaction tube and add reagents. It's not as simple as that. So what happens to it before we can put it into this electrospray to get it into the mass spec? So we need some form of purification and separation before we can put it into the mass spectrometer. So obviously biological mixtures, your serum, your plasma, are really complicated. And they contain lots of salts, lots of proteins, and lots of other interference you might want to get rid of, drug metabolites or other things that might interfere with the analysis of your compound of interest. And so we need to do purification and separation for that reason, but also mass specs, as I said, aren't infallible. They have a limited sensitivity sometimes, and they have a limited dynamic range. So the difference between, say, the concentration of the smallest or most abundant analyte and the least abundant analyte. So we have to boost sensitivity, especially if we're measuring really low abundant things, so like EGI, to get it into the range which the mass spec can do. So there are sample prep techniques we can use, which we'll talk about, and then we also need to do some form of chromatography. So for sample prep, there are some really simple ones we can do, and hopefully you might have seen these in your lab. So we do protein crutches, so this is probably as simple as it gets in terms of adding acetonitrile or zinc sulfate or something that's going to cause all the protein to crash out because centrifuge it and then create a supernatant. The problem with this is that it's really dirty. It's really cheap, but it's really dirty, and the supernatant can get spilled and contain lots of salt and other rubbish. It's gone a bit out of favour now because we don't really do GTMS anymore, but liquid extractions used to be quite good, especially for things like steroids, which are non-polar. So you can have a polar solvent and a non-polar solvent in that way. Supported liquid extractions, still quite common and popular, and then solid phase extraction, which is probably the most robust and common method used nowadays because it's gotten very cheap now. So I'll really just talk about this last method because it's important to have a grasp on. So in the simplest way possible, you could have, say, a column which contains some solvent bed, obviously sandwiched between these two discs that are going to just fall out. And that's going to have some chemistry that binds to your analyte of interest and doesn't bind to the thing you don't want. And there are lots of different chemistry out there, depending on, because you could be measuring acids, you could be measuring bases, you could be measuring everything. So we just condition the cartridge, put your sample on, and in this case, our analyte of interest is the stars, and they bind to that solvent and remain there. We can then wash all the salts out, we can wash some protein like this back in the filter. And we can do multiple wash steps to get it as clean as we like, and then we can elute our analyte off the solvent. And the key point about this is not only purification, but let's say we put in, I don't know, 5 milliliters of urine, we could then elute off, let's say, 100 microliters of evidence. So we massively concentrated that sample. So if we're trying to boost sensitivity, obviously that's going to be a benefit. So in terms of sample prep, so these used to be, I mean, you can go do this, and I've done millions of these extractions manually with these kind of vacuum manifolds, but obviously that's time consuming and subject to a lot of variations from operator error. But nowadays, as I'm sure you've seen in your own labs, we can use, just a few examples here, we can use robots to simplify this process, although if you've ever tried to program this hack, you'll know that it's not a simple process, but once you've got it working, it's great, as long as it looks great. And we can do lots of extra steps, we can do multiple extraction, there's lots of flexibility in those robotic platforms to prepare a sample. So we talked about sample prep. So let's say we've got our serum sample, we've stuck it through our solid phase extraction column, and we've extracted a mixture of non-polar compounds, which contains our gold sulfur that we're interested in, let's say. But we still need to do some chromatography on the front end with the mass spec. So that's not always the case. So for, say, newborn screening, anyone here works in the clean lab, you can just extract, say, a blood spot and then do what's called flow injection analysis, and you literally just take the whole extract and just inject it into the mass spec all in one go. But that's going to be a very complicated mixture. You might have lots of interference from things interfering with the ionization of your molecule of interest, but it's very quick. So if you're just measuring, say, female or whatever, and it's internal standard, then it's very quick to do that. And if you show you can measure it reliably, then there's no need to be controlled. But in most cases, it is important. So again, lots of GCSE chemistry in this document, but hopefully at some point in your lives you may have done paper chromatography, and it's literally just the same principle. So if we have our complicated mixture, in this case it's a spot of trouble and we put it in some sort of solvent that's then going to migrate up the paper, then sorry, I know this is a bit of a basic example, but we're going to separate out the constituents of that mix across the length of the paper, depending on the physicochemical properties of, say, the orange dye and how that interacts with the stationary phase, the paper in this case, and the mobile phase, which in this case is water or a mixture of water and acid. And that principle is exactly the same as the one we use for liquid chromatography. So this, I had to dig this out. This is a big for my thesis, but that's not all I'm doing. But this is an example of, say, a liquid chromatography machine, obviously heavily simplified. But again, I encourage you, if you have one in your lab, just go have a look and, well, ask around it first, obviously, but have a play around, look at all the bits and pieces and get a feel for what they look like. And anyone who's worked with us is familiar with but when they're working, they're great. So we've got our processed, quote unquote, purified sample. We can inject that, and obviously it can be automated. Back in the day, with Burness manual, but obviously we have auto samples to do this for us. We can inject the sample into the injection loop, and then we're going to hold it in our sample loop, and then we're going to, with a mixture of solvents, apply a gradient across time. So let's say it will start at a low concentration of water, and then the concentration of water will decrease over time, or the concentration of, here it's acetonitrile, but it could be another solvent like methanol, will increase over time. And that solvent's then going to go across some column that we've got inside the column, and then that, whatever comes off that column is going to go to the electric spray and once again. So what's actually happening in the column? And again, apologies if you already know this, but so this is a kind of classic example of reversed phase chromatography. So within this column, we've got loads of little beads, and on those beads, obviously in the schematic, we've got, so this is the C18 column, because you've got, as the name suggests, 18 carbons attached to this silicon group. But obviously we can change that chemistry depending on what the chemistry of our analyte is. So for something like metanephrines, so for plasma mets, we can use an amine column that's going to interact with the charges that those metanephrines have and separate them in that way. But these non-polar sodium phases will interact with things through, say, van der Waals forces, and that will help us separate non-polar molecules. If your molecule is really polar, so like oxalic acid or sodium acid, it might not interact at all, and it might just go straight through the column. And that kind of behavior is not necessarily what we want most of the time. So our sample is going to come to the column. Our analyte is going to bind to, well, hopefully, interact with those active groups on the column. And then as the amount of water changes in the mobile phase, our analyte then going to actually get pulled off and come out into our instrument. And the strength of those interactions will depend on the structure of the analyte of interest, obviously, so that we can separate different molecules in this way. And an important thing to realise is that these columns are not, you can actually see the scanning electron micrograph for these, but they're not, obviously we draw them as like perfectly spherical circular beads, but they're not, so they're these irregular shapes. And there are lots of mechanisms that happen in these columns that slow the path of these molecules through the column such that they enter at exactly the same time, let's say, but they will come out at slightly different times. And you'll get a distribution then of the amount of analyte that's coming out of your column. So say this analyte that's taken a long time to get through the column will come out later than a molecule that just comes straight through. And that just really depends on, as I said, lots of different mechanisms by which that happens. But that's why we get peaks at the other ends, these kind of Gaussian peaks, as opposed to just like a single line. So we've got our analyte coming off our column. It's going through our electric spray, so we've got a super high voltage vacuum applied to the other side. So obviously the pressure will be lower on this side than this side, so literally just sucking those ions in. Now normally actually we have, because there's lots of still neutral species in that electric spray, we usually actually angle the entrance to the instrument and the electric spray carry. Not quite a 90, but say like 45 or a bit higher than that. So the neutral ions will just fly off into the back of the electric spray, whereas the ions will then get sucked in at an angle so that we can get so because although we purify the sample, although we put it through an LC, it's still not going to be like a pure mixture, of course. So there's still going to be lots of stuff, especially in biological matrices, that obviously really go to. And then we can put it into our, so in this case we call it a triple quadrupole, because we've got our one quadrupole at MS1, a collision cell, which is kind of technically a type of quadrupole, and then our third quadrupole that's measuring that fragment ion from cortisol. And so overall, we're measuring that transition from 363 to 121. And usually we'll measure actually more than one. So we'll say the most abundant but still specific fragment ion we'll call our quantifier ion. So that's what we'll quantify as the amount of IOL. And then we'll measure our qualifier ion, which is another fragment that's specific to cortisol, for example, but maybe isn't a good enough signal to use to actually quantify the amount of it. And obviously we measure the same thing on like calibrators to get to an absolute concentration. And if we do that, we'll end up with a profile over time that looks like this. So we're measuring the intensity of that transition, so the amount of fragment that's reaching the detector over time. But if you remember, if the amount of analyte that's coming out changes, well then at the beginning, the analytes that come through really quickly, we'll start to see a signal. And then as we get more and more through, we measure it at the time, and we're measuring slices, because can anyone tell me why there's going to be a gap between the time at which we're measuring the intensity of this transition? Like, why don't we just measure it like constantly? Why is there a gap? It's related to the multiplexing method of that. Yeah, exactly. So in those gaps between the red lines, we could be measuring another ion. And the speed at which an instrument can do that is called the duty cycle. So modern instruments can flip between different frequencies incredibly quickly. So you can make, so you could probably reliably determine on a chronoscope to measure 10 different things at once. Back in the day, it was a lot slower. And the speed at which you do that then determines the shape of the peak you get at the end. So as we keep measuring the intensity of that transition over time, we're taking kind of samples from that peak that's forming in the electric field. We'll get something like this. And related to that duty cycle I was talking about, so the gap between these lines will then give us a different number of points per peak. And then we're going to try and estimate then what the total area of that peak is. And so the more points we have, well, then the better that estimate is going to be. So it's always a balance between, okay, how much stuff do I want to measure? Because let's say you're measuring 3 different analytes, so normetanephrine, metanephrine, 3-T, for example. For each one of those analytes, you're measuring the quantifier ion, to mention, so the most abundant fragment, say. You're measuring the qualifier ion, so the thing we want to give you more specificity, telling you that is normative you're looking at. And you're measuring the internal standard as well to get the ratio for your configuration. So for each analyte, you're measuring a minimum of 3 ions. So then you've got 3 analytes, you've got 9 ions to measure within each of these windows. And obviously the speed at which it does that is kind of incomprehensible, but it's not as simple as just measuring one thing for all of them. So yeah, we've estimated the shape of that peak. We can then integrate that with basic software to get the total area of that peak. We can then compare that to the internal standard area, and then we compare that ratio to the ratio you see in the calibrators. Obviously, through that we can get our concentration. So why do we bother with chromatography? It's also complicated when mass spec is selective already, aren't they? So the problem with these compounds is that although tandem mass spec gives us some specificity or selectivity by using fragmentation, and steroids is a great example of this. They're all very similar structured, and lots of the fragment ions will actually be the same. So these massively charged transitions will be very similar. And if you don't separate them in chromatography, because of the poor resolution of protocols and mass accuracy of protocols, you can't actually necessarily resolve those. So it's important to add a separation step at the front end to help your mass spec differentiate its compound. So this is an example. You probably invested in this nowadays, but an example of a chromatogram for cortisol, prednisone, and cortisone. So if you imagine you just chuck those all in at the same time, you just have a mixture of those steroids that your mass spec is trying to separate, and it will do okay, but you'll probably have some kind of bleed over to the signal over through. But if you do this chromatography, you can then separate it so that, obviously, if you go back to that previous example, you're measuring these transitions at these points, and at those points you just measure cortisol. And the other thing by separating things like that is that, as I said, if each analyte has 3 master charge ions that you need to measure, you can actually just set your instrument instead of scanning across all. So let's say we've set up a method to scan for cortisol, prednisone, and cortisol. At this time, you could say, don't bother looking for prednisone because I know it's not there. Just measure cortisol. Get loads of points per peak so that you get a really accurate peak shape, and then switch to measuring the transition to prednisolone here, and maybe just kind of measure a little bit here. Then switch your instrument to prednisolone, and then switch it to cortisone. And by using those windows, you can massively improve the quality of your data again, through that estimation of the true peak shape. Rather than trying to scan everything all the time. And you can do some really clever things by separating things like that. And so obviously this is an added layer of selectivity. So if you really wanted to, if you had a super complex mixture of stuff, so biological fluids is a good example, there's lots of things to test, like water samples from rivers and all sorts of kind of mixtures. You could technically do, I mean, you could do LC if you wanted to, but you could do 2D liquid chromatography, and you could do MS to the truth. So you could do mass spec. You can literally just bolt these things onto the end, or you can do it in time. So you say, measure the parent ion, then you fragment it, and then you measure the fragments, and then you fragment those fragments to do something with them, or you react them with gas to make something other compound that's selected. There's a lot of flexibility, and there are a lot of complicated techniques that you can do to add selectivity. Obviously, in a clinical lab, that's not really difficult to the kind of things we do. It's not usually measuring entire proteins, but it's important to appreciate that those methods exist and the reason why they exist. And you can fractionate samples ahead of time, so you can do like a liquid chromatography step just by itself, take those fractions off, and then measure those fractions separately with normal acid and then kind of combine all the data at the end. So that used to be a very popular technique for proteomics, for getting really, really deep coverage of really low vacuum stuff. But because of the ability of modern mass specs to get the sensitivity and informations that have improved over the last 20 years, that's not popular. So the total workload then that we've covered is we've got a sample front end, we've got chromatography, two-dimensional, but one-dimensional. We've ionized it, we've analysed the mass in some way, and we've usually done something with the ions to add an extra layer to it. And then we've detected them. And that is liquid chromatography mass spec in Portugal. So I hope that was helpful. Obviously, apologies for some of those, a bit basic, but yeah, hopefully so in terms of clinical mass spec, again, I'm appreciative of that, but obviously we can measure small molecules, as I said, drugs, immunosuppressants, steroids, other small metabolites like we can measure single protein, and I think we should probably do more of this than we are. So things like there are lots of use cases where you've got lots of different forms of a protein hormone that you need to separate. So ATP is a good example. Gastrin, which I think Tricia is going to talk about later. We've got lots of different forms or lots of different kind of NIPT and different isoforms that immunoassays just cannot differentiate. And there's lots of biology that we kind of miss by doing this. And things like insulin is another good example where you could, using a mass spec method, which is obviously more complicated, we've talked about, and takes longer, but you could differentiate the different kind of synthetic or porcine forms of insulin from endogenous insulin, and that has clear clinical relevance. So I think this will probably be more popular in the future. Paraproteins is a big use case that's becoming more popular recently. So there's new instruments that use multi-time, but it's effectively a different ionization method and a different aspect that really measure the time that an ion takes to reach a detected required tube. And there's lots of promising data on measuring monoclonal proteins with this technology that may have, I think it's yet to be proved how much benefit that has over more serious protein electrophoresis. But I think it's going to be more common to see these in use. I know Oxford having their use for the moment for doing research in the space. And then you can make mass specs much more complicated to do more complicated things. So this is an example of an Orbitrap mass spectrometer which was invented. I think it was a Russian guy who invented it, but these are exceptionally high resolution and high mass accuracy instruments that you can use to measure entire proteins. So there are a few. Over the last 20 years, there's kind of been a race to measure every single protein, say, in an organism's protein. And even when I started in this space, quite a long time ago, you could only measure, say, 3,000 proteins. And nowadays, you can literally just measure the entire protein of like a fly, which, when you get clever, that's kind of crazy that you can do that. The human protein remains complicated, but we're very close to these modern instruments. So this is an Explorers analyzer, which is the latest fancy instrument from Berlin. But I think there are other clinical biochemists working on metabolomics, so measuring the entire metabolite of the urine samples. And I think we'll probably see that as a group of Liverpool doing it on architecture urine. And these methods do have clear clinical relevance, so it's important to have an appreciation for the latest.
So right, everyone, we'll get started again. So I'm delighted to introduce the next speaker, who's Dr. Ben Jones, who's one of the consultants in metabolic medicine here at Imperial, and he's going to talk to us today about GLP-1 receptor agonists from this basic science to clinical practice. So I'll hand over to you, Ben.
Thank you very much, Matt. Morning, everybody. Sorry, I'm not there in person. So yes, I'm oh, sorry. I think there's a bit of an echo. Oh, we're okay now. Yes, so I'm Ben Jones. I work at Imperial. I'm a consultant here. I'm mainly an academic now, working on receptor pharmacology, with a particular focus on the GLP-1 receptor, which is what I'm talking to you about today. I should say that almost all of my post-CCT clinical experience has been in the lipid clinic, and I've never prescribed a GLP-1 receptor agonist in my life. Yeah, as I said, all of my research is in this area, so hopefully I'll be able to give you a bit of an overview of the science which underpins this hugely important therapeutic target. So let's see. Okay, so yeah, so just move people's faces off the screen. So yeah, last year GLP-1 was recognized as the breakthrough of the year by Science on account of its enormous impact on medicine and society, I guess. And I'm going to give you a bit of a historical overview about how GLP-1 was discovered, and how its targeting therapeutically has been optimized over many years. I'll talk to you about semaglutide, which is, as you know, is the current class leader in the GLP-1 receptor monoagonist field, obviously now being surpassed by tirzepatide. I'll talk a little bit about side effects, the mechanisms behind them and how much of a problem they are. And then I'll finish with some discussion about new approaches which are based on GLP-1, but in some cases include other receptor targets, which seem to be even better for treatment of type 2 diabetes and obesity. Okay, so starting with the historical aspect. So, I mean, really, you could go back over 100 years to start seeing for some of the very initial discoveries about the role of, I guess, bioactive substances in the intestine, which were shown to affect metabolism. Some of these were, it seemed, able to affect blood glucose, but really, from a GLP-1 perspective, it was in the early to mid 80s when this area sort of took off. And this has been recognized last year with the award of the Lasker Prize, which, as many of you will know, is the sort of the next rung down from the Nobel Prize to these three individuals here. I'll give an overview about what their contributions have been in this field. So starting with Joel Habner and Svetlana Mojsov, and then I'll move on to Lottie Knudsen afterwards. Okay, so the early work by Habner and Mojsov was, it was kind of based on previous work about understanding of the pre-pro-glucagon gene. So glucagon and the related peptides are all encoded by a single gene, pre-pro-glucagon, which was cloned and its sequence understood in the early 80s. Mojsov recognized that in this sequence, there was basically, so here is GLP-1. But yes, maybe I'll just backtrack slightly. So after making this discovery about the existence of GLP-1 in this pro-hormone, the full-length GLP-1 peptide, GLP-1 1 to 37, seemed to be completely biologically inactive when you administered it to humans or to animals. But Mojsov noticed that there was a likely cleavage site here, 6 amino acids into the GLP-1 sequence, shown just here. And she was able to show that this existed naturally in extracts from the small and large intestine. These are obviously chromatographic analyses shown here, and she showed that these two forms of GLP-1 co-eluted. Well, there were these peaks which co-eluted with synthetic GLP-1 and 1 to 37. You just turned down the volume. There was a bit of an echo there. Okay, so, and then this piece of work here, which was published in 1986, there was a lot of other data included in this paper, but essentially they were able to establish the tissue-specific processing of this pro-glucagon gene into these different forms of glucagon, GLP-1, GLP-2, oxyntomodulin, glycentin, and many of the other forms. But the critical part here was that this truncated form of GLP-1, 7 to 37, was identified experimentally in this study. So moving forward about 30 years, a huge amount of work has been done on understanding GLP-1 processing and release by the intestine. A lot of that work in the UK has been done by Fiona Gribble and Frank Ryman in Cambridge, and they've built an understanding about how different nutrients are able to stimulate the release of GLP-1 from these enteroendocrine L cells in the intestine. It's stimulated by glucose, stimulated by many other nutrients as well, in some cases via these sort of indirect mechanisms. So then going back into the mid-80s, so thus far we've shown that GLP-1 7 to 36 exists, but what does it do? So again, Mojsov and Habner were the first to show that this was a bioactive peptide. They showed here that when you infuse this into isolated rat pancreases, it's able to stimulate the release of insulin, even extremely low concentrations of sort of 10, 20 picomolar, as shown down here, 50 picomolar actually. So this was the first demonstration that this was the bioactive form of GLP-1. Shortly after that, some work was done here in the unit where I'm based here in Hammersmith, where Steve Bloom and colleagues were able to show that this GLP-1 7-36, the bioactive form, was able to stimulate insulin secretion in humans as well. And it was noted in this paper that it was possible that the insulin stimulating and glucagon suppressing effects of this peptide, which I haven't shown but are well recognized, or potentially a more active synthetic analog, could be useful in the treatment of non-insulin dependent diabetes, or type 2 diabetes, as we would call it these days. So that was the sort of early demonstration that GLP-1 was able to stimulate insulin release from the pancreas. Actually, probably more relevant to how we think of GLP-1 these days was the demonstration also here in Hammersmith by Bloom and colleagues, that if you administer GLP-1 directly into the brain of rats, it was able to suppress food intake, as shown on this graph here. And this sort of led to a huge amount of interest in this area, with a lot of pharmaceutical companies getting on board, trying to develop GLP-1, not just as a treatment for type 2 diabetes, but as a treatment for obesity as well. And that was the possibility that that might be the case was commented on in the paper. Okay, so now if we sort of move forward 30 years, there's a huge amount known about the actions of GLP-1, the physiological actions of GLP-1, because a lot of the experimental work is done in mice. It's instructive to compare the effects in humans and mice, and by and large, the effects of GLP-1 in humans and mice are the same. But just to sort of summarize some of the key ones, GLP-1 suppresses food intake, but as you will know, can cause nausea. It also stimulates insulin release and suppresses glucagon release, which is thought to be one of the means by which it improves glycemia in diabetes. Another major effect is that it slows gastric emptying, so delaying the absorption of glucose into the blood. Another reason why it improves glycemic profiles. And there are lots of other effects which are recognized, cardioprotection being of significant interest, and there's a lot of mechanistic work trying to understand whether the beneficial cardiovascular effects of GLP-1 are dependent on just its broader metabolic actions, or whether it's due to direct effect of GLP-1 on cardiac myocytes. Okay, so that's a little bit about GLP-1 physiology. How about pharmacology? So a lot of the work in this area has been pioneered by Novo Nordisk, and that was why Lottie Knudsen was recognized for her pivotal contribution to this area. So as many of you will know, the native GLP-1 peptide has an extremely short plasma half-life of about 2 minutes. And this is what you want physiologically for a hormone usually. You want something which you can switch on and switch off rapidly. And the reason why it's so unstable in plasma, well, the rate limiting step is that there's basically a cleavage point here at position 2 in the peptide where it's susceptible to cleavage by the enzyme DPP4. And that converts the active GLP-1 7-36 into the inactive form GLP-1 9-36. There are other reasons why GLP-1 is not stable in plasma, but this is the sort of rate limiting step. So again, many of you will probably know that the first GLP-1 receptor agonist to be approved clinically was exenatide. So exenatide is a GLP-1 paralog. So it has a somewhat similar sequence to GLP-1, but it has rather similar effects physiologically. And the reason why exenatide is more suitable as a drug than native GLP-1 is because it has in this position 2 a glycine rather than an alanine, and that means that it's no longer susceptible to DPP4 mediated degradation. It also has a number of other amino acid substitutions throughout the molecule, which also enhance its proteolytic stability, which becomes important once the DPP4 cleavage site is lost. However, exenatide itself still has a fairly short half-life measured in sort of 30 minutes, an hour, 2 hours, that sort of thing. And this is because once you make the peptide stable, the main clearance route is through the kidneys. And this means that for exenatide, twice daily injections are required with the original formulation. So what Lottie Knudsen did was take a different approach, and she's starting with the normal sequence of GLP-1, which is shown here. She made, she barely made any changes to the amino acid sequence. There's just one here, really, an arginine substitution at position 34. But the main difference is that it has linked to this lysine at position 26, a short linker followed by a fatty acid. And this is a C16 saturated palmitic fatty acid here. And the importance of this is that it allows it to bind to albumin in the circulation. And by binding to albumin in the circulation, firstly, it protects it somewhat from the enzyme DPP4 just by steric hindrance. But secondly, and probably more importantly, it just makes the molecule essentially much larger, and so it's no longer able to be cleared by glomerular filtration. So you go from something which has a half-life of a couple of minutes to something which can be given once a day, which is what the dosing regimen is for liraglutide. However, as you will all know, liraglutide has effectively been replaced by or at least should be by semaglutide in terms of its efficacy. So semaglutide, again, pretty similar in terms of its amino acid structure. There is a change here at position 2, which is the DPP4 cleavage site, which is where the alanine has been replaced by an artificial amino acid, AIB. So that provides a bit of protection against DPP4 cleavage. But the main innovation was to firstly make the fatty acid a bit longer, so C18 C18 fatty acid, but more importantly, it's basically a dicarboxylic acid. So one of the carboxylic acid groups is sort of used here to join to the linker, but then the other one is free here, and this is what promotes even tighter binding to albumin, and as a consequence, about sort of 99% of semaglutide in the circulation is albumin bound, as opposed to, I think, maybe around 95 for liraglutide, and this gives it a much longer half-life, suitable for weekly dosing. Okay, so that's semaglutide. I will go over a little bit of the clinical data that supports its use, because it is, in the GLP-1 receptor monoagonist space, at least the current class leader. And this is focusing on the obesity dose, so Wegovy, the 2.4 milligram dose. So here are the results, the sort of headline data from the STEP study, the STEP 1 study, part of the STEP program. This paper published by John Wilding in Liverpool 3 years ago or so. And as you can see, semaglutide produces about a kind of placebo-subtracted weight loss effect of around 12–13%. And this is sort of replicated in other sort of analogous studies using semaglutide. And you can also see, if you look at sort of categories of weight loss, which are often used to assess treatment efficacy, that, you know, if you use 5% weight loss as your treatment target, which will be enough to produce significant metabolic benefits, then almost everybody, although not everybody, on semaglutide achieves this. So a real revolution in the obesity space at the time that these data were generated. So obviously, we're not only interested in kind of biomarkers like HbA1c and weight and body weight reduction. Really, what we want to know is, do these treatments improve health outcomes? And again, as you will know, there's now almost, it feels like every month there's a new health outcome which is improved by GLP-1 receptor agonist treatment. And I guess semaglutide has sort of pioneered many of these studies because it is so effective. And yeah, so here we have the SELECT trial, which was looking at cardiovascular disease. I guess we would say maybe atherosclerotic cardiovascular disease predominantly. And the primary outcome here was this composite cardiovascular endpoint, which included cardiovascular death, non-fatal MI, and I think stroke as well. And if you include those together, you can see it's clearly there's pretty rapid divergence in the effect of semaglutide on this primary cardiovascular outcome. And when we look at, so yeah, this is heart failure. So the STEP HFpEF study. So this is using a sort of quality of life type metric for heart that's validated for use in heart failure patients. And again, you can see very clear benefits with semaglutide treatment compared to placebo in this study. And then when we look at chronic kidney disease, the FLOW study also published this year, you can see clear evidence that semaglutide is able to reduce progression of chronic kidney disease in terms of the progression to a major kidney disease event, so starting dialysis or transplant. And there were also, you can clearly see on the EGFR graphs, which I haven't shown here, that it's able to slow the decline in renal function seen in patients with type 2 diabetes. Okay, so that's a little bit of information about the benefits of GLP-1 and GLP-1 receptor agonists, semaglutide specifically. We can talk a little bit about some of the side effects now. Okay, so I think all of you will know that the main side effect with GLP-1 receptor agonists is nausea and other gastrointestinal side effects like vomiting, diarrhea, abdominal pain, constipation, all typically seen at higher rates in the active treatment compared to the placebo in the trials. So yeah, in terms of mechanisms, let me just go back, sorry. Yeah, in terms of mechanisms, so this is not easy to study in humans. So a lot of work has been done in mice. And these are sort of 3D images of brains from mice, which have been imaged using a fluorescence device. And essentially what they're showing is the distribution of fluorescent semaglutide in this magenta color, and also a marker of neuronal activation in the cyan color over here. I don't know if it's in the same mice, but it's, certainly you can look at the different areas and see where they overlap. And what you'll notice is that the distribution of the drug is fairly restricted, right? It's not sort of getting all over, it's not going all over the brain. It's particularly concentrated in these areas, such as the hypothalamus, which is here, and the brainstem, which is here. And these are sort of very much what we refer to as circumventricular organs. So they have almost not quite direct access to the systemic circulation, but pretty close to, because of the presence of fenestrated capillaries in these regions, which allow slightly larger molecules to directly exit from the circulation and activate neurons in the vicinity. So what you might notice is here is the activation marker CFOS, and there's a lot of signal here in this area, which is the brainstem, and particularly in this central part here, which is called the area postrema. There's a lot of GLP-1 receptor activation there when you inject semaglutide in mice. Now, the area postrema is well known as a brain region which is critical in mediating nausea to a number of different emetic insults, including GLP-1, cytotoxic chemotherapies, and many other sources of nausea. So it's thought that a lot of the nausea effects of GLP-1 are mediated via action in that particular area in the brain. So moving back to the clinical data, so a lot of the sort of large trials will have comments like this, which is taken from the STEP 1 manuscript, that nausea and diarrhea were typically transient, mild to moderate, and subsided with time, which I think is probably reasonable, but slightly downplays the reality. I mean, there's clearly a large excess of patients who experience GI side effects with GLP-1 receptor agonists. Typically, we'd say around 30 from the trials when you compare the placebo and the active treatment groups. And actually, when you look in the supplementary data from the STEP study, whilst they sort of describe it as being transient, it kind of gives the impression that, well, this is something that only happens when people start treatment, and then after a few days they'll be fine. But really there are a significant proportion of patients, sort of 15–20% of patients experiencing these kind of side effects throughout the duration of the trial. And so whilst for individuals it may be something which comes and goes, it's not something which is only seen at the beginning of treatment. So I think just worth being aware of that. And those of you that have used GLP-1 receptor agonists in your clinical practice, which I haven't, will probably have more of a handle on this than I do. Anyway, so yeah, around 5% of patients in this particular study in the active treatment group discontinued treatment because of the side effects. So not a huge number, but that's still a significant proportion, I would say. And that's when we look at clinical trials. Obviously, you will all know that clinical trial patients tend to be sort of more motivated. There's a bit of an incentive from the investigator's perspective to maintain adherence. And when you start looking at real world data, then the side effects can in some cases be more prominent. And obviously the real world data are also inherently limited, but they can still be instructive because they provide at least some picture of what's happening in reality. Here's some relatively early data that highlights that basically nausea and vomiting seem to be the commonest reasons why patients give up GLP-1 receptor agonists in the real world. Although admittedly, this would have been with some of the earlier generation of drugs. And then, but when you do look at some of the more recent studies at these sort of, either prescription databases or other sources of this information, then it's quite a significant proportion of patients who discontinue these drugs after several months. So, a third to a half, according to some of the US data, and somewhat similar in the UK. So, and if this proportional reason for why patients are giving up these drugs is applied to this, then it would suggest that it's more of a problem than you might think from just looking at the trial data. But yeah, many of you may have your own data on this from your own sort of internal audits, but this is an example of what's been published in the literature. Yeah. Okay, so, oh yes, and then sort of, related to this, but also to the fact that NICE will only allow us to prescribe some of the GLP-1 receptor agonists for a maximum of 2 years, it's important to highlight that when patients do discontinue these drugs, then they tend to regain quite a lot of the weight which they had lost during the treatment phase, about 2/3 over the course of a year or so. And presumably those two lines will continue to converge over time. Another sort of topic which has become sort of a bit of a hot topic at the moment in the GLP-1 field is whether this quite pronounced weight loss that patients are experiencing will lead to concurrent loss of muscle strength or sarcopenia and consequently muscle strength. So there's no question that when you lose a large amount of body weight, then you lose not only fat mass, but you also lose lean mass. Now, not all lean mass will be muscle, but some of it probably will be. So that may be a concern. However, I think there isn't really strong data that this leads to any deterioration in muscle function, at least to my knowledge. And there's some evidence that the muscle quality actually improves in patients taking these GLP-1 receptor agonists. And there are some small studies that show that at least activity-related functional status can be improved in patients who lose even quite a lot of weight on these drugs. So, probably fair enough to say that there may be some groups who are more at risk of muscle loss, and this is a reason why these drugs shouldn't be taken in an unsupervised manner. But maybe the elderly, maybe people who are frail for other reasons might be more at risk. But yeah, it's something that's often talked about. I'm not totally sure if there's as much of a problem as people say, but there are certainly a lot of pharmaceutical companies who are sort of trying to define this as a real problem so that they can justify developing treatments to maintain muscle in the face of the large amount of body weight loss that you get with GLP-1 treatments. Probably a pragmatic approach would be just to encourage people to exercise, right, and then they'll maintain their muscle mass that way. Okay, so I'm just going to move on to some of the newer approaches to target GLP-1, and there are three kind of groups of these treatments. That there are three different strategies. One is oral therapies. Another is to optimize how we actually target the GLP-1 receptor itself at the receptor level, and the third is basically concurrently targeting multiple gut hormone receptors at the same time, which many of you will be aware of is how it's thought to be one of the reasons why tirzepatide is so effective. So we already have oral semaglutide, Rybelsus. This has been generated by basically formulating it with a molecule called SNAC, which basically prevents this peptide from being broken down in the stomach and facilitates its absorption through the stomach into the circulation. So this is one way to get delivery of an existing GLP-1 receptor agonist drug via the oral route. Now, the bioavailability is still very low. It's about 1 to 2%, I think. So you have to give very high doses every day compared to what you would get just by a once weekly injection. And because of the well-known issues with supply limitation with these kind of drugs, then this is a potential bottleneck. Although I guess a lot of the supply is related not so much to the manufacturer of the drug itself, but the pen devices in which they're supplied with. But some of it will presumably be related to synthesizing the drug. So there is a lot of interest in generating small molecules. So here's semaglutide. This is its chemical structure. And here's a rather interesting new molecule called orforglipron. You can see it's a lot smaller, although it is still rather large for a small molecule, I must say. This has been developed by Eli Lilly, or at least it wasn't invented by them, but it's being developed by them. If you're interested, here is the GLP-1 receptor. Here is it's the sort of orange molecule. Here is the GLP-1 receptor itself, and then here is GLP-1 shown in this green color. And then if we look at orforglipron, referred to here as CHU128, you can just about see it here, binding in this part of the receptor. So it is engaging with the same part of the receptor as GLP-1, but it's a lot smaller. Orforglipron, it also has a rather unusual pharmacological property in terms of how it activates the receptor. So this is something which I find extremely interesting, but maybe is not that interesting to people who are mainly wanting to use these drugs just for their clinical utility, but I will mention it anyway. So essentially all receptors, all GPCRs, are subject to a process called desensitization. So you activate them, but then they will tend to become less active over time. And that's partly related to the role of these molecules called beta-arrestins, which are recruited to the receptor and kind of sit underneath the receptor here and block its ability to engage with G proteins, which are ordinarily responsible for intracellular signaling by the receptor. So what we have with this orforglipron molecule is different to what we get with typical GLP-1 receptor agonists. So basically, it's able to activate the receptor and produce a G protein response, but it doesn't really recruit the beta-arrestins. So you have this side of the signaling chain without this. So the principle there would be, or the hope there would be, that this would allow this drug to improve its ability to sort of act over time, and avoid receptor desensitization. And so it would have a larger pharmacodynamic effect for the same degree of receptor occupancy. So it's a kind of interesting mechanism, but whether it actually applies to its clinical efficacy, I guess we don't really know. But it does seem to be pretty clinically effective. These are the phase 2 data. You can see we've got at sort of 6 months, we've got pretty much the same degree of weight loss as you get with semaglutide, so about 13% placebo subtracted. So it looks pretty interesting. Okay, and then finally, we've got the targeting of multiple receptors concurrently. So the GLP-1 receptor is one of a family. It's in the class B G protein coupled receptor family, and the other sort of most closely related receptors in that group are the glucagon receptor and the GIP receptor, the glucose dependent insulinotropic polypeptide receptor. And yeah, so it's because of the similarity of these different receptors, it's possible to design drugs which are able to activate all of these receptors, not at the same time, but one at a time. So yeah, again, that's just to say these drugs don't concurrently bind to all of the receptors, but they can bind to any of them. So that means that when you use them physiologically, when you use them pharmacologically, they will engage all of the 3 receptors, or 2 of the receptors, depending on the ligand that we're talking about. And this is potentially beneficial because, as well as having the effects via the GLP-1 receptor, then there are other potential benefits which are mediated by these other receptors. So the GIP receptor may be able to, if you activate it, may be able to suppress food intake. It may, interestingly, be able to reduce nausea. So that would sort of increase the potential tolerability of the GLP-1 component of the drug. And there are lots of other potential benefits of the GIP receptor, some of which are related to adipose tissue potentially. And then the other member of the family, the glucagon receptor, is of considerable interest because not only will it potentially have a small effect on reducing food intake, it can also, it seems, increase energy expenditure. So increasing energy expenditure then tackles the other side of the obesity coin, and you can drive additional weight loss by both reducing energy intake and increasing energy expenditure. And I guess the other way to think of it would be that, well, if you've got concurrent targeting of all of these 3 receptors, you might actually be able to effectively give a slightly lower dose, and therefore have fewer side effects because you're getting the benefits of action at these other receptors as well. And the best known examples in this class would be tirzepatide, already clinically approved in the UK and the US and Europe, and then retatrutide, which is looking extremely promising and is in phase 3 at the moment, but we'll have to see what those studies show. Yeah, I'll just skip over that. I will just flag that whilst everybody thinks of tirzepatide as being, it's a great drug because it targets 2 receptors, the other reason why it may be so effective is that it shows this so-called biased agonism that I referred to earlier with orforglipron at the GLP-1 receptor. And actually, a lot of people in the field think that tirzepatide is just a super GLP-1 receptor agonist, and its GIP receptor activity is providing, very little additional benefit. But it's still an area of controversy, and a lot of people are trying to resolve this question. I will just make a point about going back to this sort of sarcopenia muscle loss question. So I mentioned retatrutide. This is this triple agonist which also activates the glucagon receptor. So there's, we've known for, I guess, nearly 50 years that patients with glucagonomas have very low amino acids, and as a consequence, they have excessive muscle wasting. And this is due to acceleration of the urea cycle by glucagon in the liver, and then sort of feeding back and extracting amino acids essentially from the muscle. So there is maybe some concern that these highly effective drugs which target the glucagon receptor as well might be more likely to cause sarcopenia. And David Hope from our lab, along with Trisha Tan, has done some interesting work in this area in the last couple of years. But I think this still remains to be seen, and it maybe just highlights the need to carefully monitor, or at least in the trial setting, for these kind of potential side effects. The final thing that I want to talk about is the amylin receptor. So the amylin receptor is another, probably the fourth major target for obesity therapy at present. Targeting the amylin receptor has been known about for many, many years, but it's really sort of validated by some of the human genetic data, which I've summarized, which is summarized here in this chart from this paper from 3 years ago, where they showed that out of the group of receptor genes, the amylin receptor gene, which is CALCR, or also known as the calcitonin receptor in this case, is one of the strongest drivers of increased BMI in humans if you have a loss of function mutation in that receptor. It's clearly not as it doesn't have as large effect as the melanocortin-4 receptor, which has an important role in monogenic obesity, but it's certainly important for sort of common increases in BMI in the general population. It's expressed in the brain. If you activate the amylin receptor, you suppress food intake. And many of you will be aware of cagrilintide, which is the most advanced long-acting amylin receptor agonist in clinical development. And this is being developed by Novo Nordisk, and I've shown some of their phase 2 data on this slide here. So essentially here they've combined cagrilintide with semaglutide, co-formulation, so they can both be injected via the same pen. They call it CagriSema, and you can see here that semaglutide and cagrilintide are reasonably effective for driving weight loss, but the combination of the two is even more effective, as you'd expect. So another potentially valuable member of the sort of pharmacotherapy armament for obesity treatment. And yes, so this is, I think, one of my final slides. So this is a very nice review from Melanie Davis's team in Leicester. And here she's summarized many of the GLP-1 based treatments which are in late stage clinical development or have recently been approved. And essentially the color refers to which stage they're in, phase 3, phase 2, etc. And then the sort of intensity of the color refers to the dosage. And on the y-axis is the amount of weight loss that these drugs have achieved. And the one which so far seems to be winning is this triple agonist, retatrutide, shown here, achieving about 23% weight loss, placebo subtracted. CagriSema, I think, is probably, I can't actually see it. Yeah, where is it? It's over here. So not quite as good, but I think that's been supplanted by some more recent data, actually, which shows that it is pretty effective. So yeah, a lot of these therapies on the horizon, all of them are based on GLP-1 as the sort of backbone. And I think, that just indicates the importance of this particular hormone as a treatment target for diabetes and obesity. Everybody wants to make a drug which is based on GLP-1, but then add something on top of that, be it amylin or GIP, such as tirzepatide, glucagon, such as retatrutide, and then you've got other things like peptide YY, which is another anorectic gut hormone. So that's everything I was going to say. Just to conclude, so I think over the past 5 to 10 years, GLP-1 receptor agonists have really revolutionized obesity treatment. And this is built on, I guess, sort of, 30 to 40 years of intensive research in this field, which has been done by a large number of researchers over the globe. I talked a little bit about side effects. They are, it seems to me, commoner in the real world than in clinical trials. So there's still probably a need to develop, newer agents, newer and better agents, which are more tolerable, or just have a larger number of examples available, because it may be that somebody who doesn't get on with semaglutide might do fine on tirzepatide. And finally, there's a lot of innovation at the moment to develop new treatments based on GLP-1, be they designed for oral administration, be they based on this concept of biased agonism to optimize how they target the GLP-1 receptor, or be they agents which are able to concurrently target multiple gut hormone receptors. And the hope is that these will lead to, firstly, greater efficacy, secondly, greater tolerability, but also, particularly with some of the orally available versions, greater access, because they should be cheaper to manufacture at least. They shouldn't need refrigeration, so they might be more suitable for a kind of global patient base. And yes, that's everything. Thank you very much, and I'm happy to take questions.
Perfect. Thank you so much, Ben. That was fantastic. And if anyone has any questions, you can pop them in the chat. And actually, there's one there already, Ben. I don't know if you can see it. It says, "Does the FLOW study include all CKD patients or just type 2 diabetes with CKD?"
I think it's just with type 2 diabetes, if I remember rightly. But somebody who knows the trial better may be able to correct me. I think that's the name of the trial. It wouldn't surprise me if there are either results available or trials ongoing to look at the effect of these treatments in patients with obesity and chronic kidney disease consequent in the context of obesity, but I don't quite remember.
And does anyone in the audience have any questions as well? Well, I think there are more questions coming for you, Ben, in the chat.
Yeah, I can. I'm happy to. Shall I take the questions in the chat? So, first question from Nesma, which is, can patients stay on GLP-1 for more than 2 years? Well, so I'll just say again that I have no direct clinical experience of using GLP-1 in the clinic, because all of my clinical work is in the lipid clinic, and we don't prescribe GLP-1s there. My understanding is that NICE say up to 2 years only, because that's what the clinical trials have or at the time that the approval was made, the clinical trial data was up to 2 years. I mean, to me, it seems self-evident that if patients stop taking GLP-1 at that point, then they will regain the weight and lose some of the metabolic benefits that they've accrued over that time. It may be the case that in the future there'll be a drive to sort of, say, okay, well, you've lost a lot of weight with this high dose semaglutide or high dose tirzepatide. Now, to sort of maintain that weight, we'll just revert you back to like a lower dose so you can maintain your weight over time. But I mean, that would be from first principles. It doesn't seem logical to me that there would be a medical reason to stop taking them just at 2 years. But as far as I know, that's the advice from NICE. That, so again, somebody else may know better. And then the other question from Marina: how do we explain differences in the range of weight loss in different patients? Some patients on liraglutide experience significant weight loss, and some patients have a poor response to semaglutide. Yeah, so this is, I personally think, is a super interesting question. So because my research is very much focused on the receptors themselves, we do know that there are a large number of mutations which can be seen in these receptors. About 2/3 of patients have at least one mutation in the GLP-1 receptor, and it's thought that may drive some of this heterogeneity in response. However, it's probably a relatively minor contributor to the heterogeneity in response that you're alluding to. But it could be drug specific, actually. You could have a receptor which responds well to liraglutide, but not so well to semaglutide, for example. But probably in reality, a lot of the heterogeneity will be related to adherence and that sort of thing. But there will also be other genetic pharmacogenomic factors related to, half-life and absorption factors and all of this sort of thing, which will contribute there.
Perfect. So our next speaker is Dr. Ralph Wigley, who's a principal clinical scientist at Great Ormond Street Hospital, and he's going to talk to us about inborn errors of metabolism. I'll hand it over to you now, Ralph.
Do I need a microphone?
I can give you. Do I put it? There. I can give you the microphone. And if you sort of stand in front of here, just okay. Maybe there as well. That's all right. Yeah, so it's a small. You can click it on your Mac as well.
Okay. Everybody hear me okay? Okay, so I'm going for a slightly different approach. So you're all going to have to be,
I'm so sorry.
you're going to have to be a little more interactive and stay awake. So I thought I'd do a case-based approach to inborn errors of metabolism. So my normal area of expertise is inborn errors related to enzyme defects, so things like lysosome storage disorders, glycogen storage disorders. So I'm a little outside my comfort zone as well. Okay, so case one, male infant, normal term delivery with a low birth weight, presented at the local hospital, data of life, acutely unwell and hypothermic. What's everybody's initial thoughts? Does somebody want to volunteer what possible diagnosis could be this early on, or what you want to rule out straight away? Or shall I start picking on people? Check the cortisol, yeah. Not bad, show. Glucose lactate, why? Sorry, I was more thinking sepsis. Hypothermia and acutely unwell. Just because I'm doing an inborn errors talk, think sepsis. Yeah, so certainly my initial thoughts would be blood gases, cultures, Usenes, definitely lactate, and an ammonia. So blood gases, somebody want to be brave and interpret? Matt, you want to have a go at interpreting the blood gases?
Activated. The PK2 is in the normal range and by carbon activated, but metabolic activated, which is not concentrated.
Partially respiratory compensated, I'd say. So, following on the next bit, cultures came back negative, the ammonia came back as 1200 and the lactate came back at 6. What do we all think is the most significant result? Ammonia, yeah, certainly for neonates, anything above 200, we want to be very, very worried about and we want to investigate further. 60 to 200, yes, we want to investigate, but certainly anything over 200 is likely to be an inborn error of metabolism. So first line investigations for ammonia. Blood gases, we've already done that, but ammonia is a respiratory stimulant. If it's purely due to a high ammonia, we'd expect respiratory alkalosis. Presence of a metabolic acidosis could suggest an organic acidemia or a fatty acid oxidation defect. Normal electrolytes, the urea is likely to be low in the urea cycle defect because the cycle is effective, therefore we're not going to generate urea. Liver function tests, fatty acid oxidation defects, organic acidemias, usually can throw out the liver. Glucose, if we're thinking fatty acid oxidation defect, the glucose is going to be low. Again, lactate raised in many metabolic conditions and in liver failure. Calcium, this is quite an important one. Certain organic acidemias will give you a hypocalcemia, generally because they interfere with your body's ability to respond to PTH. And then ketones. So if we've got elevated ketones, it rules out a fatty acid oxidation defect. Whereas if we've got low ketones, it can suggest that we've got a failure to mobilize fat and generate ketones. So this is our two-day-old's bloods. We've got an anion gap and a corrected anion gap. So my next question, what's been used to calculate the corrected anion gap? Anybody who's thinking of doing part one, this seems to be a favourite question. So I know there are at least 2 people who know the answer to this. Anybody else want to volunteer an answer? In fact, 3 people. Nope. Answer in the chat.
I thought we said albumin.
Yeah, albumin. Like calcium, most corrected tests are based upon the albumin result. Albumin's a major buffer for hydrogen ions as well, so if that's low, it will affect the anion gap. What does the anion gap indicate in this case? The rest of them? Is it normal? Is it elevated? It's elevated. Yeah.
Given how unwell and the severity of that.
Yeah. So there's a presence of an additional anion that's not being measured. And does anybody want to give me any other significant results from that? Alex? Yeah, urine ketones are elevated. Anything else? Ish. ALT is raised. Hypocalcemia, yeah. So in review, we've got hyperammonemia, metabolic acidosis with an increased anion gap, mildly abnormal LFTs, hypercalcemia, a low normal glucose, and raised urine ketones. What's everybody thinking here? Fatty acid oxidation defect, urea cycle, organic acidemia. I'm hearing mumblings, nobody shouting anything. An organic acidemia, yeah. The results suggest of an organic acidemia. So special investigations to follow this up would be obviously urine organic acids, acyl carnitines, and samples should ideally be collected starting before treatment is started. So acyl carnitine, Ed brilliantly gave a talk on mass spec earlier. This is the results for our acyl carnitine profile we ran at GOSH. We use a precursor ion scan. So we take the blood spot, we elute out the carnitines, and then we directly inject it in following a derivatization with butyric HCl. And each of the carnitine species will fragment off a small molecule with a mass charge ratio of 85, and then we do the precursor ion scan, and these are precursor ions. So this is a normal profile. This is the profile from our patients. What does everybody notice is different between the two? Other than just saying there's a lot more peaks present. Yeah, this one. So this is why INDs are horrible, because there's a lot of information in there. The essential major point is the C3 peak is grossly elevated compared to normal. We've also got the additional peaks of benzoyl carnitine and phenylacetyl carnitine. Now, this is because this sample has been collected post the patient starting ammonia scaling use. It doesn't affect the carnitines as much, it will affect the organics use. And the other peak to note is the C4DC or succinyl/methylmalonic carnitine. Again, going back to our earlier talk, these methods are not infallible, and unfortunately we suffer from isobars. So we cannot separate succinyl and methylmalonic carnitine from each other. But that isn't significantly raised. And if we look at the quantitation of these, we've obviously got the elevated C3 and a normal methylmalonic carnitine. I'll come back to why that's important in a moment. So we did the organic acids. Now, there is a hell of a lot of information and a hell of a lot of bits on here. This is done by GCMS. So, sorry, somebody's still using GCMS. Essentially, we're separating out the molecules by volatility. So the more volatile they are, the quicker they get through the column. Anybody feeling brave as to what's in here? I'm guessing not. So the key one here, I'm sorry it's not very clear, I've done the best I can to expand it without and trying to get all the information on the page, is 3-hydroxypropanate. And also we have methyl citrate. Now the reason I say pre-treatment samples are important is we can lose the methyl citrate if they've started ammonia scavengers, because you get a massive hit rate peak forming from sodium benzoate. So in review, we've got grossly elevated propanol carnitine with a normal methylmalonic carnitine, grossly elevated 3-hydroxypropanate, as well as a strongly raised methyl citrate. We've also got lactate, 2-hydroxybutyrate, and 3-hydroxybutyrate, and acetoacetate, and this is the patient's ketotic. So anybody want to hazard a guess, propanol carnitine, what the organic acidemia might be?
Well, that's the one that probably looking profile academia.
Yeah, propanoic acidemia. So when we metabolize branched chain amino acids, one of the terminal points for valine and isoleucine is the generation of propanol-CoA, which then feeds back into the TCA cycle. In propanoic acidemia, the enzyme propanol-CoA carboxylase is inhibited and leads to the formation of 2-methyl citrate, propanol glycine, propanol carnitine, and 3-hydroxypropanate through other pathways. So for the FRCPath exams, the way, because I've done this as case-based approach, certainly for part 2, module 1, you may get an inborn errors question. Typically, it's set from the approach of you're working in the DGH. And you want to know how to approach a hyperglycemic, hyperammonemic patient. I'd say probably 16 out of the 20 marks for the questions are going to be on how you'd approach it from the DGH. What samples you collect, not the interpretation of the specialist test. So it's having an idea of the basics you do, glucoses, ammonias, things like that, but also knowing what tests to do to follow up. So these are the ones I would say are likely to come up. So things like propanoic acidemia, methylmalonic acidemia, and again, as I mentioned, you'll lose the methyl citrate if you start these pre-treatment. IDA and GA, so isovaleric acidemia and glutaric acidemia, they're both on newborn screenings, just to put a couple of caveats in. Isovaleric acidemia by the newborn screening method is subject to an isobaric interference from pib oil carnitine, which if mum is taking a pivalate containing antibiotic, can cause problems. You have to follow this up with the organic acids. You don't see any interference in the organic acids, which you will do on the ASL carnitine profiles. And glutaric acid, there is this non-secretory phenotype, so you might not see the glutarate carnitine on ASL carnitines, and we'll follow this up with a urine carnitine profile to help diagnose if you have a suspicion of GA1. Okay, case 2. So this time we've got a 1-year-old female, born 37+2. Mum had maternal group B strep, so we started on antibiotics. The initial main amount of bloods showed potassium 7, so somebody decided to do a blood gas on the wall. Go on then, somebody else want to have a go at what's wrong with these blood gases? What stands out? Yoshi? Another metabolic acidosis. Anything else? Here, the muttering. Very low glucose, yeah. So metabolic acidosis and low glucose. So causes of hypoglycemia. Anybody willing to volunteer one? Or think in broad terms. High insulin. Yeah, so endocrine causes. So things like hyperinsulinism, adrenal insufficiency, hyperpituitarism, growth hormone deficiency, hypothyroidism. Any others? What am I talking about? Inborn areas of metabolism. So metabolic causes, things like fatty acid oxidation defects, disorders of carbohydrate metabolism, disorders of organic acid metabolism, or disorders of gluconeogenesis. And then you've got the other causes. So neonatal complications, things like prematurity, infants of diabetic mothers, drugs. Insulin is a drug. Hyperinsulinism is one cause, but giving somebody too much insulin is also another. And then you've got things like sepsis, multiple organ failure, and tumours. And then there's also idiopathic ketotic hypoglycemia, which is one of the most common causes of hypoglycemia in young children rather than neonates. And it's generally set off by a mild illness. So, first-line investigations for a hypoglycemic patient that should be done while the patient is hypoglycemic before we do any corrections. Obviously, you want to repeat that glucose point of care. Sorry, that isn't as reliable as a lab glucose. 3-hydroxybutyrate and 3 fatty acids. If we've got hyperinsulinism, we expect these both to be suppressed. Insulin suppresses lipolysis, and therefore no lipolysis, no free fatty acids, no ketone generation. However, if we've got a fatty acid oxidation defect, we've got that lipolysis, so we're generating free fatty acids, but we're unable to generate the 3-hydroxybutyrate. Lactate, if they're hypoglycemic and they've got a high lactate, this can suggest a gluconeogenic defect. C-peptide, probably should have put that under the insulin. I did. So you need to measure this along with the insulin, and we've all seen the news recently about the Lucy Letley cases. One of the arguments is that we weren't measuring the insulin properly, we weren't looking for C-peptide, so how do we know that this was exogenous rather than endogenous? So measuring the C-peptide should match the insulin. If it doesn't, it's suggested that the insulin is an exogenous source. And then obviously we've got our other endocrine causes measuring the the cortisol and the growth hormone. Further tests to do post-correction, measure the lactate again. I'm going to start there because glycogen storage disease is what I do on a daily basis. But an elevation of lactate post-correction of hypoglycemia is suggestive of a glycogen storage disorder because you put glucose back into the body, it's already got glycogen stores, so the body just converts it down through the glycolytic pathway to lactate. Urine ketones will be absent or inappropriately low in fatty acid oxidation defects. And then obviously numerous metabolic conditions will give you deranged liver function tests. GSD is again another example. And blood gases. So we've got unexplained acidosis with increased anion gaps, again, acidemias. So back to our patient. So the laboratory glucose came back as 2.1 with an elevated lactate of 3.8. We're all thinking of gluconeogenic defect at this point? No? The rest at least. No? Cortisol and growth hormone, cortisol 600, sorry, I've got the units. Growth hormone is 8.5 micrograms per litre. Ammonia is 60. Worried about that? Or is it a bit borderline? Has the sample been collected properly? Certainly worth having a repeat. Insulin and C-peptide are both low. The non-esterified fatty acids and beta-hydroxybutyrate. So the non-esterified fatty acids 3.4 and the beta-hydroxybutyrate is 0.11. And there's also a bit of family history. I had a sibling that died shortly after birth of an unknown cause. So the insulin and C-peptide are both appropriate for hypoglycemia. How's about the cortisol and growth hormone? What do we think for those? They look appropriate. don't forget these samples were taken when the patient is hypoglycemic. I'd say yes, they are. Stress response. So there's no obvious endocrine cause. The fatty acids to 3-hydroxybutyrate, that ratio is not normal. You would expect the beta-hydroxybutyrates to be almost double the free fatty acids, so that ratio is and the family history does point towards an inherited cause. And I'd say that given we've got hypo, we've got that disturbed ratio of the free fatty acids to beta-hydroxybutyrate, we're looking at a fatty acid oxidation defect. So tests for fatty acid oxidation defects, again, very similar to organic acidemias. Acyl carnitines, now to note, there are two possible sample types. There's blood spots and there's plasma. Plasma is better for picking up CPT2 deficiency, whereas blood spots are better for CPT1. All others, it doesn't matter, it's whatever sample type you prefer. Again, organic acids, with this time we're looking for glycine conjugates for some of the disorders, presence of the dicarboxylic acid urea, or in this case, the lack of 3-hydroxybutyrate in superacetates that we're expecting with fatty acid oxidation defect is these should be present. And then we can do more specialist testing. This is typically done up in Sheffield in this country, where they take fibroblasts and they feed them radio labels, fatty acid, and monitor the flux through the pathway. So again, back to our normal carnitine profile. This is the one from our patient. Few more peaks present. Does everybody notice? It's towards the right side of the screen. So we've got C16 hydroxy, C16 hydroxy, C18 1 and C18 present that weren't there in the normal profile. And if we look at the concentration sheet, you can see they are significantly elevated. So slightly nicer looking organic acid profile, they find there's a lot less peaks. However, we've got 3-hydroxy adipates, we've got 3-hydroxy decindioate and 3-hydroxy dodecindioate, and some 3-hydroxy adipate present. So these are all dicarboxylic acids. We're also absent 3-hydroxybutyrate, which you run there, and C2-acetate. So there's no ketones being generated, and we've got a dicarboxylic acid urea. So fatty acid flux studies. These are always performed on 2 separate days. They're feeding C14, which is mysterate, C16, which is palmitate, and alanate, which is C18 and C81. So in this case, hopefully you can see that there is significantly lower activity with the longer chains. Certainly with C18 and C16 compared to C14. So, in conclusion, we've got elevated long-chain hydroxyl carnitine species. So this is either going to point to a long-chain hydroxyalkyl dehydrogenase deficiency or a mitochondrial trifunctional protein deficiency. Very similar with the organic acids. We've got the dicarboxylic acid urea, again, the flux studies. And mutation analysis is shows the patient is homozygous for a mutation in HADHA, which is the long-chain hydroxyalkyl dehydrogenase deficiency. So final diagnosis, LCHAD deficiency. So the high lactate, to go back to that, isn't because of a gluconeogenic defect. 3-hydroxy C16 inhibits PDH. So this is where the lactate is generated from in this case. Typically fatty acid oxidation defects, you wouldn't see the lactate. So this is the beta oxidation pathway. So in this case, for our patient, we've got loss of the hydroxyalkyl dehydrogenase, the long-chain specific one. I mentioned mitochondrial trifunctional peptide deficiency. This is where you've got the loss of both the enol hydratase and ketothiolate. This is because for the long chains, these form a single protein complex. and mutations in either HDA, HA or HADHB prevent the formation of this complex. So you get the L shadow-like picture in the cases, though the long chain species are slightly less raised because you've obviously disrupted the profile at the hydratase there as well. So follow-up. 2 years later, mum presents to a local hospital for a routine checkup. She's 17 months pregnant. The obstetrician thought she looked slightly puffy. And when she was questioned, she stated she often had swollen ankles. The following results were obtained. So can somebody comment on the results without making a diagnosis to begin with? Raised ALT? Yeah. She's 7 months pregnant. For the creatinine, that would certainly be a dilutional effect, but yeah, the albumin. So, what further biochemistry does anybody going to want to do? Oh, Marissa. Bile acids, yeah, that would be one. Urine protein. Yeah. Central growth factor. Does anybody think we should do any other laboratory tests other than biochemistry? Now, this is a big point for exams. When you see further laboratory tests, don't just think biochemistry, think other labs as well. Nothing, any suggestions? Or blood count, yeah, including platelets. So, as you mentioned platelets, Bethan, what are you expecting to see and why? Or what does it help stand for? Hemolysis, so you see hemolysis, elevated liver enzymes in low platelets. Evidence of hemolysis and low platelets. I'm slightly out of order. Okay, and again, similarly for the exam, I would say you need to know these ones. Just have a rough idea of what you should be seeing. Certainly for part one, there are questions based on you've done a sarconatine profile, you've seen elevated C14-1, what's the disorder, and I know that they have in the past in part 2, module 1, put a mag in. Okay, final case for me. This time we've got a 12-year-old female, previously well, no background history of note, however, developed a sudden pain in the back of the legs and difficulty walking, which resulted in a fall at school. So she's sent home to rest, no improvement in pain or mobility, so taken to a local hospital. At the local, no viral symptoms, no pain anywhere else, no weakness in her upper limbs. She was able to walk on her tiptoes by this point. However, when she passed urine, it was bright red in colour, so obviously routine blood's taken. So these are the initial bloods. Sam, what stands out? Yeah, creatine kinase of nearly 200,000. It's quite significant. Top 2 is also negative. Yeah. So the red urine, I think we can all assume is myoglobin, elevated or grossly elevated creatine kinase, suggestive of rhabdomyolysis. This is the creatine kinase over the next couple of days. It drops down, but it doesn't actually normalize. It remains around about 5,000. So this is the MET bionet suggested algorithm for the investigation of rhabdomyolysis. So you want to exclude non-metabolic causes, e.g. infection, inflammation, toxicological causes. Do a clinical examination looking for neurological, cardiac, gastrointestinal, ophthalmology and audiology, especially if we're thinking respiratory chain defect, and then first-line biochemistry investigations. So repeat the creatine kinase and deoxygenase, lactate, amino acids, acyl carnitines, and the blood spot POMP, for urine, organic acids, and CSF lactate if you're querying respiratory chain defect. And then you want to consider additional non-invasive testing, things like exercise testing, including forearm exercise test, EMG and ECG. So the patient wasn't aware of any particular trigger for the episode that she'd had, other than she'd had PE earlier in the day. Parents were consanguineous and had aunts that were wheelchair bound since they were teens. Wheelchair user. Clinical team sent samples for blood spots for POMP, entomology, acyl carnitines, as well as plasma sample for carnitine analysis, repeat using these in a full blood count. So the POMP came back, POMP entomology came back normal, and the plasma and blood spot acyl carnitine analysis came back unremarkable. And the reason we've done the plasma is because we're looking for CP2. Oh, we can. Yeah, not a bad show. Since the first episode, patient's muscles felt weak after only 2 minutes of exercise. So it's a shortened exercise tolerance, which is more sort of heading towards a myopathic glycogen storage disorder. So one of the better tests for doing this is a forearm exercise test, unless you can go through the genetics. So this used to be ischemic. They changed it because of the major complications of contractures and the risk of triggering another episode of rhabdomyolysis. Essentially, the patient is fasted from midnight, avoiding exercise for 30 minutes before the test. They're cannulated and then allowed to rest for further 10 minutes. And baseline samples are taken for lactate and ammonia. They're then made to exercise until exhaustion by squeezing the sphingomanometer bowl. Even a normal individual, this is going to hurt. Doing it maximally for that sort of time. And you then collect subsequent samples for lactate and ammonia at 1 minute, 2 minutes, 4, 6, 8, and 10. And the samples need to be processed immediately. And at the end of the exercise, the patient should be checked for contracture and flexibility of their fingers. In a normal individual, both the lactate and ammonia should rise 3 to 5-fold greater than the baseline. If failure of the rising lactate indicates a defect in the glycolytic pathway, either glycogen breakdown or the actual pathway itself. Whereas a failure of ammonia to rise is the myoadenylate deaminase deficiency. So this is the one from our patients. Then we have a go at interpreting. The orange is the ammonia, the blue is the lactate. So somebody on the chat has suggested McArdle's disease. Yeah, one possibility. So certainly we've got a greater than 3-fold rise in ammonia, so the patient's worked sufficiently hard. If you don't see the rise in ammonia in the lactate, then the test needs to be repeated. The patient hasn't worked hard enough. In this case, we've got a failure of the lactate to rise, so it definitely points to a defect in glycolytic pathway or glycogen breakdown. Patient also had the full blood count done. Anybody feeling brave enough to have an interpretation of the FBCs? Anything particularly stand out? Low hemoglobin. Yeah. Microcytic yeah. Yeah, reticulocytosis. So possibly a hemolytic anemia, the low hemoglobin, the low hematocrit, the raised reticulocyte count, and the low MCV, all complement to hemolytic anemia. So what routine biochemistry abnormalities would we expect to see? I'm going to pick on you. Okay, the low hemoglobin. Yeah. Raised unconjugated bilirubin. So bloods were sent for a GSD screen. So we measure the glycogen content in the erythrocytes, the phosphorylase B kinase, the white cell phosphorylase in both the total and the active form, and then we ratio them, and the white cell debenture. So all results within the reference range, doesn't indicate a glycogen storage disease covered by the screen. However, most myopathic GSDs, you can't pick up in blood, you have to use muscle analysis. So somebody on the chat suggested McArdle's. The hotspot mutation, which is in preferred testing in the UK, came back negative. So it's unlikely to be McArdle's. Full metabolic myopathy panel found no mutations at all in PYGM outside the 2 hotspot mutations. It did, however, find 2 mutations in ablase A. So, ablase A deficiency, it's rare, in about 70 cases in the literature. Typically presents with a hemolytic anemia, exercise intolerance, cramps, muscle pain, and rhabdomyolysis. So this all does fit clinically. And we did the biochemistry, and that also fits. So it's a GSD12 or ablase A deficiency. So the reason I brought that one up is the 4-on exercise test is just a good way of introducing the case with it in, has frequently appears across all formats of the exam. Certainly regularly features on part 1. It's certainly in the last couple of years featured on part 2, module 2 and module 1. So I would say if you're revising for this exam, definitely cover the basics: hypoanemia, hyperglycemia, and hyperbilirubinemia. A great resource for this is the MetBioNet website, the best practice guidelines. And that's it from me. Any questions?
So hi everyone, welcome back. I hope you all had a nice lunch. So our next speaker is Dr. Segler, who is one of the consultants in metabolic medicine here at Imperial as well. And she's going to talk us through some cases from the lipid clinic, which I think are very interactive session. So I'll hand over to her.
Okay, thanks, Matt. Okay, so hi everyone. So Imperial College Healthcare we've got various sites, but we're obviously at Charing Cross, but this in the middle is the Hammersmith Hospital, which is where the first lipid clinic in the country was. So years ago, 1960s, when people thought about cholesterol, they weren't 100% convinced that it actually caused atherosclerosis and was related to heart disease. It was all about fats, and there was this big debate particularly amongst cardiologists at Hammersmith about whether it was fats or sugars that were the issue. And clearly now we know that both are an issue in causing atherosclerosis. So I'm going to just we've got I think 7 or 8 cases that I'm going to go through. No?
Does that work? Or
No.
that's right.
Yeah. Oh, perfect. This one? Yeah. Okay, great. Okay, so first case is a really straightforward one. So 59-year-old man, he's been seen by his GP, he's a barrister, and he's completely asymptomatic, so no cardiovascular symptoms whatsoever. And he doesn't have a family history of any premature cardiovascular disease. And the GP does routine blood tests on him, and this is the lipid profile that he gets back. So the total cholesterol is 7.2, yeah, which is, I think most of you would say that's pretty high. The HDL is 1.4, LDL cholesterol is 4.1, triglycerides 1.4, okay, and our reference range in our lab here is less than 1.7 for fasting sample. And the non-HDL cholesterol is 5.8 millimoles per litre. So first thing to say is, what do we mean by non-HDL cholesterol? And I think you all know very well that most of your cholesterol is carried by these lipoproteins that go around in the blood. Okay, and we've got the HDL here, which has the most cholesterol, seen in yellow here. So it's very cholesterol rich. And then all of these other ones have varying amounts of cholesterol, reducing as the size of the particle gets bigger. We've got LDL cholesterol here, and LDL particles here, got LP little a, IDL, VLDL, and then the chylomicron remnants right here at the end. And all of these are associated with ApoB, okay, ApoB 100, chylomicrons ApoB 48. And all of these in this red box are individually atherogenic in their own right, okay? So when we think about the way we measure cholesterol, we can either look at total cholesterol, which tells us about the cholesterol contained by the HDL as well as all of these other particles, or we can think about non-HDL cholesterol, which is basically the total cholesterol minus that HDL cholesterol. And the reason this has become more popular over recent years is that when we look at epidemiological studies, it looks like non-HDL is a better predictor than LDL cholesterol in big populations. And this is just one example of this. This is from a study called the EPIC Norfolk study. And you've got women here and men on this side. And each of these are sort of quintiles of non-HDL cholesterol. You can see that highest quintile in purple has that highest cardiovascular disease incidence. So that's when, I think it was now 10 years ago, NICE in 2014 decided to adopt non-HDL cholesterol as part of their lipid guidelines. And they said we should be aiming to get the non-HDL cholesterol in primary prevention below 40%. We should reduce it by at least 40% from baseline. And that was difficult because, all of the guidelines until then had been based on LDL cholesterol, and all the clinical trials for the drugs, all the statins and all the newer drugs that we now have available are all based on LDL cholesterol endpoints. So we're kind of left in this quandary where the GPs are thinking, should we be using non-HDL cholesterol? Should we be using LDL cholesterol? And different guidelines tell us different things. And actually, in practical terms, we need both these measurements to assess our patients. So does this guy need a statin? What do we think? On the basis of that, these results, if they were your results, would you be worried? Do you think he needs a statin? Should we say yes? Do we think yes? Or do we think no? Not sure? Is it one no? And I probably haven't given you enough information to make that decision, because actually all I've really given you is a bit of family history, his age, and his lipid profile. And actually we need to look at his global cardiovascular risk. So we need to put his numbers into a risk calculator, and that will tell us what his risk of having a heart attack or a stroke in the next 10 years is likely to be. And what NICE tell us to do, and also the Joint British Societies, is to offer someone a statin if they have a 10-year risk of having a heart attack or stroke that's above 10%. So, and they suggest offering atorvastatin 20 milligrams as a starting point for these people. So obviously, before we do that, and before we use the calculator, we need to rule out secondary causes of hypercholesterolemia. And the common ones that we think of, certain drugs, so particularly things like antipsychotics. We see a lot of raised cholesterols with some of these antipsychotic drugs. Hypothyroidism, nephrotic syndrome, and anorexia, particularly in young women with untreated anorexia, cholesterol levels can be very high, and we occasionally see them up to 14, 15 millimoles per litre in our patients. So we also don't use this risk tool in secondary prevention in patients with type 1 diabetes, with CKD, or with familial hypercholesterolemia, because it underestimates the risk. So this is what the calculator looks like. This is what the GPs have on their system as well. And basically you put in all of the details date of birth, ethnicity, BMI, cholesterol levels and blood pressure, and a few other factors. And then it gives you your heart age. So remember, he was 59, but his heart age is 66. And I find this really helpful with patients because you can say, well, look, you're this age, but your heart's this age, and it makes people think twice about it. And what we can also do is then tell him that on average, his risk of having a heart attack or stroke over the next 10 years is 11% if you don't die of anything else. So he's sort of on that borderline range. So we would have that shared sort of decision making conversation with him about whether or not he wants to start something to lower that risk. And what's also quite useful is you can put in an intervention. There's an intervention arm here. So, you know, the total cholesterol, you can see with 20 milligrams of atorvastatin, we'd expect it to go down by about 40%, or go down to 4.1. And his risk would then decrease from 11% to 6.4%. So that's also quite helpful in that conversation. So next question, what target lipids are we aiming for? So we talked a little bit very briefly about what NICE suggests, and in primary prevention, they don't have a target as such, which is really annoying for patients because patients like to know a number that they're sort of aiming for. But it talks about reducing it by more than 40%. So that's what we're trying to do for these patients in primary prevention. In secondary prevention, NICE have come after a lot of lobbying from lots of specialist societies and the GPs. NICE have said, okay, aim for an LDL of less than 2 or a non-HDL of 2.6. So you can see here now that we've got both of those parameters there, the LDL cholesterol and the non-HDL cholesterol. But the problem is, you know, this non-HDL cholesterol still, a lot of our newer drugs, because they're expensive, are based on thresholds at which you're eligible for them. And all of those thresholds based on the clinical trials, which is all LDL cholesterol based. And with familial hypercholesterolemia, obviously we still need LDL because this is a disorder of LDL metabolism. So we need to make sure that our lipid profiles have both the non-HDL cholesterol and the LDL cholesterol available. And then just to show you a bit more sort of what's happening internationally, we have the European Society of Cardiology guidelines, which doesn't really separate people into primary and secondary prevention. It's not this sort of this binary thing, because actually there's a lot of people out there who haven't yet had a heart attack, but they're at very high risk of having a heart attack, and they probably have a lot of subclinical atherosclerosis, so a lot of furring of their arteries already. So what are they? Do they count as primary or secondary? It's still really up for debate. So ESC talk about risk stratifying patients as sort of very high risk, moderate risk, or low risk. And they give LDL cholesterol targets based on where your risk level is. And just to show you what these risks are, so it's quite interesting because very high risk is anyone who's got documented CVD, clinical or on imaging. So, you know, very high risk, and going back to that parameter, they're talking about getting the LDL to less than 1.4 millimoles per litre. So quite a difference to what NICE are telling us, which is less than 2. Remember, ESC is a scientific guideline. It's based on sort of the best available science, whereas NICE is science plus cost effectiveness. And that's where they've come up with their parameter of 2. But all the QOF and things that the GPs will base their payments and income on are on NICE. So the GPs are really looking to get the LDLs less than 2 in secondary prevention. Though NICE do say, you know, the lower the better. So don't de-escalate if you get to less than 2. So there we go. So we talked a little bit about statins. We said that we would probably, on balance, offer this chap a statin. His risk of having a heart attack or stroke over the next 10 years is 11%. So these are the statins that we have available in the UK. Okay, the most common ones that are now used are atorvastatin and rosuvastatin, and they're the most they're high intensity statins, and they're both off patent, so they're very inexpensive for the NHS. Simvastatin is pretty much not used anymore, and NICE say actually deprescribe and swap to atorvastatin if possible. And it's particularly at the higher doses, there's increased risk of rhabdomyolysis. And Fluva and Prava, again, we used to use these a little bit more frequently in the past, but they're very weak as it goes. So they're much more likely to be, when you look at patients' notes and things, you'll see Atorva or Azuva come up much more commonly. And the other thing I just wanted to draw your attention to was, if you're on 10 milligrams of rosuvastatin, you can see that you get a 43% reduction in your LDL cholesterol. And if we double the dose, you only get a 5% extra reduction, and doubling again, only a 5% extra reduction. So actually, even at these lower doses, you get really, really good reduction. If that's all your patient can tolerate, then that's still worthwhile. And sometimes better than risking starting at a very high dose and then stopping it completely. But you'll know probably from talking to family and friends that there's a lot of mistrust about these medicines, and a lot of people are very worried about taking statins because there's been a lot of mixed media reports about them. And this is because they are the most prescribed drugs, and they're also the most well-studied drugs. So the number of RCTs that have been done on these drugs in both primary and secondary prevention is just remarkable compared to any other type of drugs. So, but despite that, you still have people like the BBC, you know, causing a lot of worry amongst patients. So how do we get around this? Well, it's a difficult one, because the clinical trials tell us one thing. They say that, you know, side effects are the same both in the placebo and active arm, and you know, actually a lot of these side effects are not real. But is this true? When you talk to a patient, they say, well, no, I felt this. I started the medicine and I felt like I had muscle pain. So a couple of years ago, we did this trial in our lipid clinic, and we basically had patients who had said, I'm, you know, having problems with the statin. I'm getting some muscle side effects within a month or so. And so what we did was we said to these patients, okay, well, let's work out, is this really the statin that's causing the problem, or is it the taking a tablet? And so what we did, we gave them these 12 little jars, and four of the jars, so 4 months, had atorvastatin 20 milligrams in them, 4 had placebo, and 4 were completely empty. We mixed them all around, so they knew when they had the empty jars, but they didn't know when they had, whether it was placebo or an atorvastatin month. And we gave them all an iPhone, and every day they had to mark their symptoms as to how bad their symptoms were. And so everyone had 4 months of nothing, 4 months of placebo, and 4 months of statin. And at the end of this study, after the year, we could unblind each patient. This was an N of 1 study where we could show them whether their symptoms were worse with the statin, the placebo, or nothing. And I think you can probably predict the results. But yeah, symptoms were definitely lowest in the no treatment arm, but they were very, very similar in the placebo and statin arm. And this was really useful for patients to actually see their own, you know, do their own N of 1 trial and say, actually, okay, I'll take the statin because clearly I'm having the symptoms with the placebo. Unfortunately, we can't do this for all of our patients, you know, do a 12-month clinical trial, but it's, you know, studies like this that we're trying to do to really try and negate all of the stuff that, you know, people hear in the media about statins, because actually, despite all of the progress that we've made in terms of new drugs against LDL cholesterol, these are definitely the best research and safest and most cost effective for us at the moment. So there has been a lot of improvement in terms of drug development in this field. For a long time, we had statins and ezetimibe, but over the last few years, there's been a lot of new medicines licensed. And this is just a cartoon showing you where these major drugs sort of work. So if you think of a hepatocyte, we're in the liver, and you know the bedrock of our treatment is still the statins here, okay, blocking HMG-CoA reductase. And then just upstream from this is this newer drug called bempedoic acid. And this works on this enzyme called ATP citrate lyase. So upstream, same pathway. And both of these, they deplete your intracellular cholesterol, and thereby this leads to sort of increased LDL receptor upregulation and recycling. So you can mop up more LDL that's sort of floating around in the blood. And then back, so out of the liver into the gut, we have ezetimibe here, which which reduces your intestinal absorption of cholesterol. Okay, and all three of these drugs, the ezetimibe, bempedoic acid, and statins, are all small molecules. And then on this side of the diagram, back in the liver, you can see these newer agents. This one, these are the PCSK9 monoclonal antibodies, and there's two of them. There's evolocumab and alirocumab. And what they do is block this protein called PCSK9, you can see here in purple, whose job is to really chaperone the LDL receptor to degradation. So if we get rid of PCSK9, if we mop it up with an antibody, you get less degradation of the LDL receptor and more recycling of the LDL receptor. And then lastly, most newly, we've got this siRNA, a short interfering RNA to PCSK9. And this is called inclisiran. This has been now around for about 3 years. And the way this works is it's a double-stranded RNA, and it's specifically taken up by the hepatocyte. It's got this moiety on it called GalNAc. So it binds the acylo-glycoprotein receptor, gets selectively taken up by the liver, and then binds the mRNA against PCSK9, silences it, and shuts off production. So you don't produce the PCSK9. It's a bit like turning off the tap. So we'll talk a little bit more in some of the cases that are to come about how these drugs, and I'll show you how these drugs work, and I'll show you a couple of cases where we use them. Okay, so that's just a little bit of a summary of the medicines that we're using for LDL lowering. Case 2. So we now have a 19-year-old gentleman. He's been referred to the lipid clinic by a plastic surgeon. So he's noticed to have these lumps around the eyes. He's fit and well. In fact, he's very fit. He's a professional footballer. And his dad, unfortunately, had an MI at 40 and then died at the age of 46. So if we look at his lipid profile, it's quite marked. You can see that his total cholesterol's 10. HDL is 1.4, LDL cholesterol's 8.3, so also very, very raised, and the triglycerides are normal at 1.1. So here he's got pure hypercholesterolemia, he's got very high LDL cholesterol. And I think hopefully you will see these stigmata, the xanthelasma there, as well as those high LDL levels, and you straight away think that this might be familial hypercholesterolemia. Obviously, we talked about those secondary causes that we'd rule out first. And I didn't mention it on there, but the ketogenic diet, particularly in young men, is really, really important to ask about. But with this guy, you know, he's young, he's fit, he's got very strong family history. FH is very high up on the differential there. And so with familial hypercholesterolemia, it's an unrecognized, potentially fatal, but treatable disease. So we know the genes that are involved, and our normal gene panel has there's 5 main genes that we look at. It's very common. We think it's about 1 in 250 of the population who have FH. And the main problem is that premature cardiovascular disease ensues in these patients. So 50% of men will have an MI by the age of 50. Very treatable. We've talked about statins, but we've got lots of other medicines available to us now as well. And it's really, really underdiagnosed. So when we look at our registries in the UK, we think we know about 4% of cases of FH in the country. So 96% of people are walking around without knowing that they've got the condition. And often they'll be picked up. For most people, they have their first cholesterol check at the age of 40, when you have your NHS well check. By then, for a lot of these people, it's too late because they've already got very established atherosclerosis, or if they're really unlucky, they've already had a heart attack. And the other way that these people are picked up is if they unfortunately have already had a heart attack and then they come onto the ward and someone measures their cholesterol and notices it's very high. So there's a lot of work to be done in finding these people, and we have to be proactive and think more about prevention rather than waiting till the problem happens and then dealing with it then. So as I mentioned, mutations in the LDL receptor or ApoB or PCSK9, and there's also a newer mutation or variant that's in ApoE that also displays an FH phenotype that's now part of our panel. Any of these variants lead to only 50% of the LDL receptors on the liver being functional. So you have less receptors to mop up the LDL. So you've got more LDL cholesterol around the blood, getting into the arterial wall and causing premature atherosclerosis. So the way we manage this is firstly with lifestyle. So these patients really should never smoke. And we've got a couple of FH patients who smoke and end up with really horrible peripheral vascular disease as well as coronary disease. We talked about some of these drugs, lots of different agents that we have available to us to try and lower the cholesterol. A lot of patients, particularly the young ones, they say, well, you know, I'll try with lifestyle. I'll lead a really, really good lifestyle. I have really, really, really good diet. But unfortunately, it doesn't cut it. And it's really important to tell these patients that, you know, this is genetic, this isn't your fault. And actually, you need help with some medicines as well to bring that cholesterol down. And then for those with very progressive disease, despite all of these other drugs, we can consider LDL apheresis. And so in terms of the potential benefits of diagnosing this early, if you look at this patient here in green without FH, they reach their kind of cardiovascular disease threshold, say at the age of 55. And this is sort of cumulative LDL. It's a bit like, it's the area under the curve of the LDL, a bit like smoking pack years. Whereas if you've got a patient with heterozygous FH, there you can see that in blue here, that trajectory is much steeper, and they're going to reach that same threshold at 35 years. And then a homozygous FH, this is going to be reached, you know, in early teenage years. And if we focus on the heterozygous FH patients, if we start statin early, we can deviate that trajectory to bring them to sort of a more normal trajectory and normal threshold. And obviously there's other risk factors take play as well. Okay, case 3. So this is one of my patients. This is patient F. Okay, she's 29. She was found to have xanthomas at the age of 2, and her total cholesterol was 29 at the age of 2. She's been on statin since the age of 5. And we've apheresed her since the age of 6. And despite that, unfortunately, when she was 19, she was pregnant, and she had some chest pain during pregnancy and ended up then in her second pregnancy requiring a PCI, primary cutaneous coronary intervention. And she also has aortic disease. She's also got bilateral carotid plaques, and she's got stenosis. She's just she's waiting a carotid endarterectomy as well. So she's got very, very severe atherosclerosis at a young age. This is her husband, and they come from the same community, and he's a heterozygous, so he's has the same variant as her, but has just one inherited from his mum. So he has FH as well. So she's homozygous, he's heterozygote, and their son is an obligate heterozygote. And unfortunately, their daughter, who's now age 6, is a homozygote. So she's inherited, obviously, from mum. She's got one of mum's variants, but she's 50% chance of inheriting dads, and she has inherited dads. So she undergoes apheresis at the Evelina on a weekly basis. And this is what lipoprotein apheresis looks like. So this is one of our patients. And this is something that the NICE recommend being considered in all homozygote or compound heterozygote FH patients early on. And in children, you know, by the age of 5, but no later than the age of 8. There should be a conversation about undertaking this. And this is one of our patients. You can see his Achilles tendon here, and this is the xanthoma that he had. And a lot of the homozygotes really suffer with, you often see them come into clinic with slippers because they just have really, really uncomfortable Achilles tendons. And you can see after 6 years of apheresis, this has come down really nicely. And it's quite a nice barometer for patients to see, because if their cholesterol is coming down from their tendons, we're hoping the same is happening in their arteries, but it's really nice for them to see these melt away. And so homozygous FH is clinically suspected when the LDL cholesterol is greater than 10. And it's due to two major defects in LDL metabolism. And patients have these tendon xanthomas, so often over the knuckles as well as the Achilles, but they also have cutaneous xanthomas over the face, but also over the buttocks and the backs of their legs. You often see these quite marked xanthomas. Often they'll have coronary disease in childhood. And when you really take the family history, they will say that they've had a sibling potentially who's also had early onset disease. And the prevalence of this is 1 in 250,000. We've had some recent guidance from the European Atherosclerosis Society on how to manage this condition, and it's rare, but it really is something that affects these young people, very severely. And so what we do is we start with the statin and ezetimibe, the usual drugs. Within 8 weeks, we try PCSK9 monoclonal antibody therapy. Unfortunately, for a lot of these patients, if they've got null mutations, null variants of the LDL receptor, these therapies don't work so well because none of their LDL receptors are either being produced or are functional at all. And so after that, we can then consider apheresis, and with or without some of these newer agents, which I won't delve into, but limiptide and ANGPTL3 directed therapy are newer drugs that are independent of the LDL receptor, and can really help reduce the LDL in these patients. Okay, so that's a little bit about homozygous FH. Turning to triglycerides. So this is case 4. Got a 25-year-old lady. She's got a total cholesterol of 5.2. So pretty normal. Triglycerides are 14, and we talked about less than 1.7 is what our lab report is as normal. HDL cholesterol is 1.1, and her non-HDL cholesterol is 4.1. So we're wondering, why has she got such high triglycerides? What is the cause? And see, we want to rule out secondary causes first. So we look, is she diabetic? Is that the reason for this? And no, her HbA1c is 31, so it doesn't look like she's diabetic. Is she profoundly obese? Is this related to insulin resistance? Her BMI is 22, so that's not the reason either. Is she drinking a lot of alcohol? No, she's a teetotal. She's teetotal, so that doesn't seem to be the issue either. And then finally, is she on any medications that can predispose hypertriglyceridemia? And the one that to really watch out for is Roaccutane, particularly in these younger people. You can get very, very severe hypertriglyceridemia. And our dermatologists now always measure baseline triglycerides in these patients and then 3 months after starting Roaccutane. So with severe hypertriglyceridemia like this, we're thinking more about the particles here on the right. So the chylomicrons, the VLDL, and occasionally IDL, but that's usually an equimolar rise in your total cholesterol as well as your triglycerides. And so in terms of primary causes, the way I think of them is triglycerides only. So like this lady, where she's got either familial chylomicronemia syndrome, or which is where you have a sort of a monogenic cause for your high triglycerides, or familial hypertriglyceridemia, sometimes now called multifactorial chylomicronemia syndrome, which seems to be a more polygenic entity. And then mixed dyslipidemias, where you have a high cholesterol and a high triglyceride. Here, in terms of primary causes, we're thinking more about familial dyspeta, or also known as type 3 hyperlipidemia. And that's predominantly an issue with IDL, with raised IDL. Or we're thinking about familial combined hyperlipidemia, which for many years people have been hunting for the gene causing this. And again, it doesn't seem to be one gene. It seems to be more of a polygenic disposition. So these patients often have very lipemic serum. So you can see this sort of very turbid serum here. Sometimes it can be, there's quite a bit of hemolysis in there, so you can get this sort of strawberry milkshake type appearance. And these patients, actually all of these patients can have these eruptive xanthomata. So familial chylomicronemia syndrome traditionally, we thought of this as lipoprotein lipase deficiency. And so autosomal recessive condition where you have two variants in the LPL gene. And this was thought to be 1 in a million of the population. But we now know that there's lots of other genes that are really involved in this. And a lot of them are anchor proteins of lipoprotein lipase. And there's a gene panel that can be done, Bristol do it, of 12 genes causing monogenic hypertriglyceridemia, which we, as a totality, we're still calling familial chylomicronemia syndrome. And so this is really a failure of chylomicron clearance from the blood. And in its most severe form, it can present in childhood with eruptive xanthomata and recurrent pancreatitis. And the thing is, the more we're looking now, we used to think it was 1 in a million. It was just because we were picking up the most severe cases and we didn't really have access to genetics. And now that we do, we're picking up much milder forms of this. And for example, we had a lady who's now in her early 30s, and she only really got picked up. She never had pancreatitis, but she got picked up in her pregnancy when her triglycerides went up to 100. And she then, someone thought, gosh, is there a genetic cause for this, or is this just pregnancy? And after pregnancy, her triglycerides were still very raised at about 20, and this condition was suspected. But actually, she's had quite a benign course because she hasn't had pancreatitis. And we plasma exchanged her during that pregnancy to ensure that that she didn't, that the triglycerides came down. But, it's becoming more and more clear that this is a spectrum of disease rather than that very, very severe phenotype that we used to see in childhood. And so in terms of the treatment, acute treatment, so if someone comes in with acute pancreatitis, we want to make them nil by mouth, and we want to just reduce any, sort of severely restrict the amount of fat going in via the diet. In terms of drug therapy, if their liver function, kidney function are okay, then we can think about starting fibrates, omega-3 fatty acids, and statins to bring down those triglycerides. Insulin increases and stimulates lipoprotein lipase activity. So often for these patients, we think about doing a fixed rate insulin infusion. Often you have to be really careful because obviously a lot of these are non-diabetic patients, so you really need to make sure you're monitoring their glucose really, really, really carefully. Heparin also increases your lipoprotein lipase. And in people who have really bad pancreatitis, it's not recovering, their triglycerides are still really high after a few days, then we can think about plasma exchange to physically remove the triglycerides from the blood. So that's in the acute phase. And then in the non-acute phase, we're really thinking about, getting them to see the dietitian, really making sure they're on a really good low-fat diet, and then drug therapy, as we talked about before. Okay, how are we doing for time? Yeah, I've got a few short cases just to talk about some of those newer drugs that we were that we discussed. So this first, no, before that, we're going to talk about something else. Okay, we're going to talk about Lp(a). So case 5, this is a 57-year-old lady. She's got a background of fibromyalgia, and she had a PCI in 2022. This is secondary prevention. And we look at her, if you look at her, her risk factors, there's nothing really that obvious that comes to fore. She's got quite a noisy family history. So her dad's had an MI at 59, her brother's had a PCI at 62, but she's not particularly overweight. Her blood pressure's okay. EGFR looks fine. She's not got any inflammation. CRP is fine. Her lipid profile is not ideal, but it's not horrendous, and her HbA1c is normal. So in this case, why has this lady had premature cardiovascular disease? And this is someone we would, in our clinic, think about measuring lipoprotein (a) in. And Lp(a), if we look at these EAS guidelines, they talk about 125 nanomoles per litre as being elevated. And that sort of equates to the 83rd percentile. In the UK, the Heart UK statement, we talk about more than 90 nanomoles per litre, equating to the 80th percentile, and also being at that increased risk of cardiovascular disease. Remember, people love to talk about something that's normal and elevated, but actually in real life, it's a risk continuum. And, obviously the higher your level is, the higher the risk. And so her levels, you can see 355 nanomoles per litre, exceptionally high. And this puts her in the 99th percentile for her Lp(a) concentration. And the difference between Lp(a) and LDL, which we talked about before, is that your levels stick with you for life. So they are predominantly genetically determined. Everyone's levels are 90% genetically determined. And this is an autosomal co-dominant pattern of inheritance. So your levels are reflected by the levels of mum and dad. And so if we look at this lady here, our patient, her concentration of Lp(a) was 355 nanomoles per litre. Fortunately, we don't know dad's levels. But her brother, who required stenting at an early stage, also has very high concentrations, and her sister here is unaffected. And we can be proactive, and we can think about, her having had premature cardiovascular disease, thinking about measuring it in her kids, who both also have very high levels of Lp(a). And if you look at the distribution in the general population, you can see it's very similar amongst men and women. Most people have these very low concentrations here. And then there's this tail of people who have much higher concentrations. And you see the risk of cardiovascular disease goes up as your level goes up. And so how does Lp(a) do this? It's very much like LDL in that it's proatherogenic, and it contains, ApoB, is seen here, this blue ribbon here. This is the ApoB, and it gets into the arterial wall and causes smooth muscle cell proliferation and builds up that lipid-rich necrotic core. It's also thought to be pro-inflammatory, so a lot of oxidized phospholipids live on the LDL, the Lp(a) particle, and there's an increased inflammatory cascade that occurs with Lp(a). And if you compare a particle of Lp(a) to a particle of LDL, this seems to be 6 times more atherogenic and more inflammatory. You see, we have much less Lp(a) in our blood than we have LDL, but on a particle-to-particle basis, this is much more atherogenic. And then finally, it's got this, what makes it a bit different to LDL also is this apolipoprotein a, which you can see here in these red and blue circles. And this has sequence homology to plasminogen, and is thought to compete with plasminogen. So Lp(a) reduces plasminogen activation and increases platelet aggregation, at least in vitro. So it's kind of seen as this sort of triple hit particle, where it's proatherogenic, inflammatory, as well as thrombotic. And so a few years ago now, we came up with this a consensus statement on Lp(a) from Heart UK. And we talked about specific groups of patients in whom we thought this would be really useful to measure. If you look at the European guidelines, they talk about measuring it in everyone, but we felt that we were really not quite far away from that in the UK. And so the people that we thought would most benefit from measurement are people with a family history or a personal history of premature cardiovascular disease, or if they've got a first-degree relative with very high levels, anyone with a genetic dyslipidemia, anyone with calcific aortic valve stenosis, and we know that Lp(a) is a risk factor for calcific aortic valve stenosis as well. And then people with a borderline increased 10-year risk of having an event, whereby, just like that first chap that we saw, that barrister, whose 10-year risk was 11%, and he may say, oh, I don't know if I want to go on a statin, for the rest of my life. If you know the Lp(a), and that's also very high, then that's going to make your, that's going to really help with your decision making to say, actually, let's just start the statin earlier rather than waiting. And in terms of treatment, the management of people with high Lp(a) at the moment is just reducing their overall atherosclerotic risk and controlling their dyslipidemia, offering a statin early on to lower the LDL, because unfortunately there's no pharmacological treatments that lower Lp(a) at the moment. And in those with that really severe disease, which is progressive, very high Lp(a) concentration, you can think about lipoprotein apheresis. So in terms of Lp(a), there are quite a few new drugs that are in development, and they're in phase 3 clinical trials. And hopefully next year we may have some answers about robustly lowering LP(a) using sort of genetic-based treatments, so siRNA-based treatments and antisense oligonucleotide-based treatments to lower LP(a). And the clinical trials so far are really promising. They're showing 90% reduction in LP(a) concentration using these drugs. So, one more? Yeah, okay. So very, very quickly, I'm just gonna, maybe I'll just talk to you about inclisiran, I think, just to show you this newest agent and why I think it's quite exciting, because in terms of short interfering RNA therapies, there's nothing really out there that we use in the NHS as a, quite frequently. There's one that's used for acute intermittent porphyria. There's one for a hereditary form of amyloid. And then there's inclisiran, which has been licensed for LDL cholesterol lowering, so for cardiovascular disease, which is obviously a much, much broader group of people. And as I mentioned, inclisiran is a small interfering RNA, limits the amount of PCSK9 you produce, and therefore it allows you to upregulate your LDL receptors. And so this is just one of our patients. He's a 59-year-old man. He's white British. He has a mixed dyslipidemia, and he's got secondary prevention. He's had a STEMI in 2021 and then a stage PCI thereafter. He's got other risk factors. And from the lipid clinic, you can see that he was on atorvastatin 80 and ezetimibe. And then when inclisiran became available, we added this on top. And you can see pre-inclisiran, his LDL was 3.9. After adding in the inclisiran, this was 1.1. So he had a 71% reduction in his LDL cholesterol. So that's been a real success for him as a treatment. And the really nice thing about this is that because of its mechanism of action, you give the injection at 0 months, then 3 months, and then 6 monthly thereafter. So it's a 6 monthly injection that the patient needs, and then they don't need to worry about it, and they know that their LDL is being lowered by it. They do need to continue their background therapy. And so, just to give you some data from our clinic, this is we now have about 300 patients on this medicine since nearly 3 years now, and just to show you, this is patients with FH and non-FH, mean age of 64 from the clinic, a really mixed group of patients in terms of ethnicity, typical in our West London clinic. 83% of them had coronary disease and 17% of them had cerebrovascular disease, and their starting LDL was 3.5. And here's the data. So you can see this is just after one dose, one injection of inclisiran, and you can see that these are the individual patients. You can see that they go down very nicely. And whether you have FH or not, you get the same reduction in LDL, which is very reassuring. And this is a waterfall plot. So each of these lines represents one patient and their LDL change from baseline. This is, remember, just after one injection. And you can see there's quite a bit of variability in the LDL reduction that you get. But when we quiz the patients on this end, where you've actually got an increase in LDL, this was because they'd stopped their baseline therapy. So it's really important to counsel a patient to keep going with their baseline statin, because a lot of the media have touted this as an injection against or a vaccination against cardiovascular disease, which it isn't. They still need to continue with their baseline therapy. I'm going to stop there. Thanks. Thank you, Matt.
Does anyone have any burning questions for Dr. Figler before we move on and on the group?
Is there criteria in which you select patients?
Yes, yeah, they're very strict criteria because of cost. So it's NICE. So NICE tell us that we can use it in people who've had a heart attack or stroke or cardiovascular disease, and they have to have a persistent LDL above 2.6 millimoles per liter. And yeah, so on maximally tolerated statin, and then yeah, on top of that,
they are statins not lowering, but if you remove the statin, you just add the inclisiran.
I guess they start with an even higher LDL. That's the thing. So despite the statin, their LDL is still. So these are patients who started on a statin. So their LDL will have come down by 40%, but it's still above 2.6. And there are quite a lot of patients like that around. And so despite that maximally tolerated statin, the LDL is still 2.6, and that's when we can think about offering this. But it's a kind of conversation about this versus the monoclonal antibody versus ezetimibe. So there's a few different options, but patients do find this really, really convenient because it's just a 6-monthly injection.
What is the cost?
Oh, massively more expensive. So a statin is about £4 a month. It's so cheap, whereas these are more like £2,000. Yeah, £2,000 a year or so, something like that. There's a confidential discount that the NHS England have with the company that make it, but it's about £2,000 a year, much more expensive.
And we've got a couple of other questions.
Yeah.
So the first one is whether you think about undertaking cascade screening for Lp(a) and logistically how you do that.
Oh yeah, that's a great question. So we don't do official cascade screening. I think the problem is with Lp(a), it's still in its infancy in terms of awareness amongst general practitioners, cardiologists, stroke physicians. So everything is done really within lipid clinics, and I don't think lipid clinics have the capacity to do formal cascade screening for Lp(a) at the moment. It's not like FH, where if you have FH, then your kids would have a 50% chance of having FH. So but in people, we talked about those specific groups of patients. If you have someone in the family who's got very high levels, or you've got a strong family history, that's when you would consider doing it.
Someone else has asked, is it okay to lower how far you lower LDL? Is it okay to lower to 0.6, for example?
Yeah, so because of these great new drugs that we have can lower LDL much, much more than previously possible. People have worried, gosh, what if I lower it too much? And there's really good data now, like using the monoclonal antibodies and things, getting them to less than 0.5 millimoles per litre, and it doesn't seem to affect steroidogenesis or your sex hormones, cortisol, any of that stuff. And yeah, there doesn't seem to be any sort of threshold at which you start getting the benefit from a cardiovascular perspective stops. So there's a really good study called GLARGL, which looked at the actual arteries, and they did angiograms, and they showed that the lower you got the LDL, even if it got to like 0.2, 0.3, the reduced risk you got of regression, plaque regression, and that there was no sort of threshold at where that benefit stopped. So yeah, so the answer is no. There's no worry about low LDLs.
Perfect. So I think we'll finish there. Just because we're running a bit of time. Thank you so much, Dr. Segler. Perfect. If you've got any other questions, you can email me, and I can pass them on to Dr. Segler for you. Right. So the next speaker is Professor Trisha Tan, who's a professor of endocrinology and diabetes here at Imperial as well, and she's going to talk to us about neuroendocrine tumours. So I'll pass over to her now.
Thanks, Matt. Okay, right. So neuroendocrine tumours and gut hormones. So I hope by the end of this short session, you'll understand what neuroendocrine tumours are, what gut hormones testing involves, and how we apply this in the diagnosis of neuroendocrine tumours. I'm very happy it's such a small group, so to be interactive, so you can put your hand up halfway through and ask questions. I don't mind. Okay, so neuroendocrine tumours are sometimes also now called NENs, neuroendocrine neoplasias. The tumours derive from neuroendocrine cells, and the way we classify them depends where they arrive from. So gastroenteropancreatic GEP NETs are the most common ones. So for instance, you've got the foregut NET between the gastric and duodenal, then we do one midgut, D2 to right colon, hindgut, transverse colon to rectum, and pancreatic NETs. Okay, and also you would have heard the terminology carcinoid tumors, so they tend to be GEP NETs. But you've also got the non-GEP NETs, so such as the lung, bronchocarcinoids, thyroid, adrenal, sympathetic nervous systems, ovarian and renal, etc. They're less common than the GEP NETs. And how do we diagnose NETs? Well, it depends which order. And often what we're seeing now is that these are being picked up either incidentally or, at surgery, etc. But the main modes of diagnosis is histopathology. That's the gold standard for diagnosing NETs. When we do immunostainings, they're very specific for the neuroendocrine markers such as chromogranins, synaptophysin, neuron-specific amylase. So you can get those on immunostaining. But the nice thing about histopathology is also it allows you to grade the tumors, and we also look at the proliferation index and mitotic index. So Ki67 is one of the way that we look at the proliferation. So if you've got high Ki67, tends to be more high grade, and this is not as good. Sorry, it's very cold, isn't it? Are you guys cold? Yeah. And then the other modes of diagnosis is imaging, cross-sectional imaging, and the number of cross-sectional imaging we do these days. We're picking up, tumors right, left, and center. So I think NETs are certainly being picked up much earlier. And there are certain imaging characteristics that are very typical of NET, sometimes also through ultrasound. And then we tend to proceed to doing more functional scans, such as gallium-68 dotatate scans these days. These are scans. Do you guys know what a gallium dotatate scan is? Heard of it? It's basically they're like a form of ultrascan. You basically have a ligand that's confined to the ultra-tide receptor. So very a bit more specific than others imaging for some of these NETs, especially when they're small. And then we have the biomarkers. Okay, gut hormones are not the only biomarkers that we use for NETs. There's also 5-HIAA and chromogranins. Now, I've put screening here in brackets because in general, gut hormones, unless you're thinking about a functional tumor, which we will go into, we don't tend to do the gut hormone profile as a screening tool. This is where we go wrong. And often, I get the emails or phone calls going this, and people chase these abnormally raised gut hormones unnecessarily for years, and then causes a lot of anxiety for patients. Okay, it's a useful biomarker, the gut hormones, for follow-up and off treatment, diagnosis of functional syndromes, and localization. And I'll hope to give you some examples. So, but as part of the diagnosis of NETs, it's really important to bear in mind that NETs can be part of the hereditary endocrine syndromes. So the history taking is very important, and you need to think about the presence of other endocrine diseases in patients and family members. Can you think of what are the other type of endocrine disorders that you might want to think about in NETs? Hypercalcemia, hyperparathyroidism is one aspect. Pituitary tumors is another. So if you see someone with a suspected, say, pancreatic NET, but also had a history of previous parathyroidectomy for hyperparathyroidism, think about MEN1, yeah? Medullary thyroid cancer, MEN2, if they've also got PO, think about the MENs as well, or or the other SDH, paraganglioma syndromes, etc. Okay. As we're going to be talking about gut hormones, I'm just going to take you through what the characteristics of gut hormones are. All peptides released from neuroendocrine cells in response to luminal and neural stimuli, but it's not restricted to the gut. These gut peptides can also be neurotransmitters. They tend to all act on G-coupled protein receptors, and we group them into families based on similarities. So you can see here, gastrin and CCK family, motilin family, ghrelin and motilin. Ghrelin's a hunger hormone, secretin, VIP, GIP, proglucagon family, glucagon, GLP-1, GLP-2, oxyntomodulin, and the PP4 family. Have you guys heard of these peptides? Yeah? Okay. Feel free to just put your hand up and ask questions if you want. These gut hormones all have lots and lots of different functions. Okay. They can affect gut motility is a big function of the gut peptides. Metabolism, you know, GLP-1 is an incretin hormone. Yeah. Do you know what an incretin hormone is? So when you eat, okay, your gut will release things like GLP-1, oxyntomodulin. These hormones then, and GIP, they then act on the beta cells, stimulate insulin release. So that's called them incretin hormones. Yeah, hormones that then stimulate insulin release after eating. And they can then control metabolism, which is why, for instance, GLP-1 treatments are used to treat diabetes. Okay, but these hormones also have other functions on appetite. They also signal to the brain, to your satiety centers to say that you're full. Okay, and they the hormones also affect secretion of, for instance, you know, after eating, the exocrine pancreas stimulates the release of some of the enzymes, etc. And as mentioned previously, also neurotransmitters. So they are multifunctional. They have overlapping functions, and they can work in the gut and CNS and elsewhere. Okay, it's a very interesting group of hormones. At Hammersmith Hospital, we run the SES gut hormone laboratory, and these are our in-house radioimmunoassays. So we have a panel. Okay, so when you click gut hormone requests, you get chromogranin A, B, gastrin, vasoactive intestinal peptide, I'll refer it to it a bit, glucagon, pancreatic polypeptide, and somatostatin. Okay, if you can also ask for CART, which is cocaine and amphetamine regulated transcript, but only on requests. And neurotensin, we rarely do now because it's only very few indications that we will need neurotensin. Okay. And I've listed calcitonin and insulin and C-peptide as well, because those are all part of some neuroendocrine tumor screen. And I couldn't remember what our calcitonin assay was. Do you remember? Is it? It used to be diazorin. It's still diazorin? Yeah. Okay. Anyway, so neuroendocrine tumors neuroendocrine tumor markers essentially are released by a wide range of neuroendocrine tumors. Okay, and I'm going to first take you through some of the general markers first, and then we will go through some examples of the more specific functional tumors. It's a little bit complicated, so I would say, you know, your take home is, you know, when you look at, I want at the end here, you'll be able to just say, if someone comes to you with a raised chromogranin A, what your thoughts are, versus, you know, the functional tumors, which are a little bit easier to handle. Okay, so we'll first talk through these three general markers: 5-HIAA, chromogranin A, B, and CART. So, and just to say, CART was originally identified in the brain, but released by NETs, and not routinely currently used because we feel that it doesn't actually have any added benefit, apart from sometimes I think in fears and paraganglioma trying to monitor the progression. So 5-HIAA essentially is a metabolite of serotonin, primarily secreted by midgut and hindgut GEP nets. It's less sensitive for pancreatic and bronchial nets. Liver metastasis must often be present before you get elevation of 5-HIAA because of the first pass metabolism of this. And 5-HIAA is associated also with a high risk of carcinoid heart disease. So how do we measure this? Well, through 24-hour urine collections. It does, there are sort of plasma serum 5-HIAs being developed at the moment, but it's not widely available and still requiring lots of validation. But for the urine, in the context of, so when you do any of these tests, your pre-test probability has to be there, okay? And if, you know, I've got a strong suspicion of carcinoid syndrome, then the sensitivity of the test is about 70, but specificity 90%, versus if I'm just randomly screening someone with a bit of flushing, yeah, you're going to get a lot of false positive results. And you can get lots of false positive results if they don't avoid eating foods that contain other amines, things like avocados, bananas, plums, walnut, pineapples, tomatoes, aubergines. We ask them to stop taking this for at least 24 hours beforehand. Okay, so if you got a non-specific elevated results, make sure you've gone through what the patient's been eating beforehand. So that's 5-HIAA. Then chromogranin A, it is a useful diagnostic marker for neuroendocrine tumors, but I would say not a good screening marker. Yeah, but it can also be elevated in other non-NETs. So things like, you know, neuroendocrine differentiations within prostate cancers, we sometimes see that chromogranin A also is elevated. It's a useful prognostic marker. And we often see an elevated CGA associated with higher tumor burden and often indicate shorter time to progression and reduce overall survival. It's actually a very, very useful marker for monitoring treatment. So, you know, when you start people on somatostatin analog treatment, or you've taken out the tumor, or you've given them radionuclide treatment, you know, and the chromogranin A drops, it's a very useful way for us to monitor response and recurrence. But, you know, there are caveats to, oh, someone's raised their hand. So oh, is that an old hand? Okay, I'll let Matt read that whilst then you can tell me. Oh, I can view.
You can click X, no, what would you?
Oh, close X, okay, right, okay. So you need to, lost my chain of thought, that's right. Okay, so you can get false positive elevations of chromogranin A if you've got liver or renal impairment, untreated hypertension, pregnancy, you're on glucocorticoids. So we see that often. We get calls and then we go through the patient list, and they are actually been given steroids and they've been in hospital unwell with X, Y, and Z, and then they sent off also a gut hormone profile because they're not sure what's going on with the patient, etc. But then when they're off treatment better, we repeat it, it's all normal. But you can also, under certain conditions, such as achlorhydria, atopic gastritis, get falsely raised gastrin, and PPI inhibitor can also falsely elevate some of the gut hormone profiles. Is measuring chromogranin A easy and uncomplicated? Well, unfortunately, the tumors do produce various chromogranin A isoforms, which makes it sort of sometimes slightly difficult, depending on your method of measurement. At the SAS lab at Hammersmith, you can see here, ours is what we call pancreastatin immunoassay, but different companies, Cisbio, DACO, etc., have different approaches for their assays targeting different epitopes. So depending which assay you use, you will get different results. Over a decade ago, we did a comparative study, and you can see here, this is controls. This is non-neuroendocrine neoplasias, and these are NETs, okay? And in general, our assay has less false positive compared to some of these other assays, but you can see that the pickup of nets, the range is very variable compared to the different assays. And to add to the complication, I must say, all these assays use different units as well. We use picomoles per liter, they use this one's micrograms per liter, you know, etc., millimoles per liter, etc. So there's it's, but at the end of the day, you know, they are, you know, they are assays that can pick up chromogranin A. And I would always advise just stick to the same assay, whatever you do in the same patient. Yeah, because in terms of, you know, the ROC curve shows, you know, the diagnostic performance is fairly similar. But the correlation between all the assays are pretty poor. So no one perfect assay for chromogranin A. One assay for chromogranin A is about as good as another for diagnosis. There's no comparative study has been made on assays in terms of prognosis and treatment monitoring. I mean, certainly for us at Hammersmith Hospital, we have that data for our cohorts because we've always stuck with our in-house assay. And I would say whatever it is, you stick to whatever you use. If you use multiple assays on a single patient at every time point, it does actually improve diagnostic sensitivity, but it's going to be expensive and most of us won't do that. So just to cover chromogranin B briefly, the performance is fairly similar to chromogranin A, but it appears to be more sensitive for pancreatic nets. CART, as mentioned previously, is useful for detecting progressive nets. It's got a reasonably better sensitivity actually compared to the other gut peptides for the diagnosis of pheochromocytoma. But because we've got plasma metanephrines, which are more sort of specific and sensitive, we rarely use CART for pheochromocytomas. And it's elevated, but it's useful in cases that are a little bit tricky. You know, we think someone's got pheo, but we're not really sure, and it's not quite secretory. CART can be useful, but again, it's not specific. And in small studies, we've shown that it's a good marker for progressive disease in terms of the pheos and paragangliomas. So it's not routinely used, lots of false positives, but if you do need it, we can run it for you. Yeah. So those are the sort of more general markers. Now we're going to just talk more specifically about the gut hormones and pancreatic nets. So a third of pancreatic nets, a third of the nets are GEP nets. Majority of the GEP nets are non-functional. Yeah, so they don't really secrete anything, tends to present with either mass effects or late at diagnosis with liver metastases. And chromogranin B can be a useful marker. But the functional tumors, GEP nets, often present earlier because of the hormones that they are secreting. Okay, and at this point in the functional tumors, the gut hormones can be useful to diagnose these syndromes. And what are the syndromes that we think about? Insulinoma, gastrinoma, lipoma, glucagonoma, somatostatinomas, and PPOmas. Very, very rare. In terms of insulinoma, you know, there are multiple criteria that we have to fulfill to diagnose. You need to fulfill Whipple's triad clinically, so symptoms of hypoglycemia, whether it's neuroglycopenia, so like kind of funny turns, fits, blackouts, autonomic symptoms, sweating, etc. Confirm evidence of low blood glucose, and relief for symptoms when the glucose is normalized. So if you correct it, yeah, so those are what we refer to as Whipple's triad clinically. And then what we would then do is also do a 72-hour fast, and this often confirms hypoglycemia with inappropriately elevated insulin C-peptide, negative sulfonylurea screen, so to show that they're not taking a drug that is causing this, and low ketones. And if you fulfill clinical diagnosis, confirmed on 72-hour fast gold standards, we go on to do imaging, okay? And different imaging have different sensitivity and specificity, and this is a Exendin 4 scan, so targeting the GLP-1 receptors. But we don't, it's been experimental for many years, hasn't really translated to clinical use, to be quite honest. Okay, any questions before we do a case? Still awake? Yeah, okay, good. Okay, first case, 24-year-old lady presents episodes of shakiness, feeling unwell, symptoms relieved by food. Ambulance did the capillary glucose when she was unwell, 1.6. Does she fulfill Whipple's triad? Okay. Okay, because capillary glucose, the sensitivity or point of care is not great, is it, that low end? Agree. Okay, but otherwise, if all of this was real, she fulfills the Whipple's triad, right? Okay, so what do we need to do next? A, 72-hour fast, B, CT of the pancreas, MRI of the pancreas is C, octreotide scan, or do a arterial angiography and calcium stim. Who wants to choose a 72-hour fast? Just Anna? 2, 3? Okay, so, okay, maybe a few of you do something. Who wants to do a CT scan? No one? MRI? Ultrascan? Calcium stim? Okay. 72-hour fast. Yeah, we want biochemical confirmation properly first before we proceed. Okay, so we had one first step biochemical blood glucose hypoglycemia, be it point of care. Yeah, but ideally we want a venous glucose, but pragmatically sometimes we don't have that. So she had a 72-hour fast, capillary glucose 1.5, lab glucose 1.4. Insulin elevated in the context of low glucose, but C-peptide also elevated, yeah? Because you need to watch out for when your insulin's up, but your C-peptide suppressed, then you need to think about, what do we think about then? Exogenous insulin, yeah? So someone giving themselves insulin. And then she had negative ketones and sulfonylurea screen negative. So, biochemically confirmed insulinoma, yeah? And we look for a C-peptide, an insulin C-peptide ratio of 1 to 10, yeah? Roughly. So in this case, you can see there 45 to 450. Again, you've got to do units to units. That's why I change it to picomoles per liter here. Okay, and I just want to show you some data. So that's biochemically confirmation. We're going to move to the next step. This is just some audit data that we've done internally. Okay, so for 72-hour fast, what is the glucose target that you should reach? In our Endo Bible, we talked about 2.2, 2.1, but you can see here sensitivity 78, specificity 96. So always depends on the pre-test probability when you undergo the test. The Endocrine Society guidelines, goes for 3, but under such circumstances, you're going to have a high false positive rate here. So I think, it's a compromise. And so we looked at this data, and I would say, you could improve your specificity around 2.6. So that's just some interesting data that I found interesting. And then same with insulin C-peptide data. Based on our audit data, we feel that actually C-peptide, can be actually useful in terms of as part of the diagnostic criteria. Currently what we tend to look for is an insulin cutoff greater than 6, but you can see that on its own, it's not, as sensitive, as specific as we would like. So anyway, 72-hour fast, needs to be interpreted carefully. It's a test that needs to be supervised, so patients do need to come in. So it is an expensive test. And I think based on our audit data, I can show you, I mean, we're currently still using 2.2. Certainly we wouldn't follow the Endo Society of 3. I think we'll get lots of high false positives. But cutoffs for insulin C-peptide, may need to be modified. We need more data around this. Okay, so that's insulinoma. Any questions? So with that patient, once we've biochemically confirmed, we go for localization. And then if we localize the tumor, it's resection. Okay, and we are getting very good at diagnosing. I mean, I remember 20 years ago when I was seeing insulinomas, they were patients that were very unwell, super obese because they eat and eat. That's what they do. Nowadays, when we diagnose insulinomas, we diagnose them so early, they're actually skinny. They haven't actually reached that point. It just shows how we've actually advanced in terms of our diagnosis. Plus, we do so many scans, we're picking things up before it becomes really a problem. So that's how medicine's changed in the last 2 decades. Anyway, next functional tumor, I'd like to talk about gastrinoma. Okay, so it causes a syndrome called Zollinger-Ellison syndrome. This is a condition where you get excess gastrin stimulated at acid production. And patients can often present with recurrent gastric ulceration, diarrhea, etc. And localizing around this area, what we call our gastric triangle. Okay, and how do we diagnose it? Well, we get a raised gastrin. Okay, but you need to make sure that patients are off the proton pump inhibitor or the H2 antagonist. And upper GI endoscopy verifies polyps and ulcers, but you need to exclude achlorhydria, high gastric pH. Okay, do you know what that is? Okay, I'll talk you through that in a bit. And what it is essentially if you've got someone with achlorhydria, you essentially you often see it in atrophic gastritis, and patients are often treated with TPI, but they don't need it. Okay, and you can take them off. And it's really important to differentiate this from gastrinoma, okay, because both conditions causes high gastrin. One way you can do this is either do something called secretin test, but it's quite hard to get hold of secretin, so we rarely do these days. Or you actually do an endoscopy and then you measure the acid output. Okay, someone with achlorhydria has a high pH versus a low pH. Okay, so we'll try this case. 60-year-old epigastric pain, referred as gastrin was measured and was 237 picomoles per liter. Does this patient have Zollinger-Ellison syndrome? What should you do? Right, who's going to do a secretin test? Who's going to repeat the gastrin level? You're the DB at the end of the phone, they're asking you, what should we do? Will you tell them to do a CT scan? Or how about take a drug history? Who's going to do a drug history? Yeah? Who does do it? Yeah. And obviously not an endoscopy just yet. Yeah, take a drug history. So this patient was not taking a proton pump inhibitor, but is taking an H2 blocker for epigastric pain. So we advised the DB, I said, stop the H2 blocker and then come in for repeat tests. But that advice should actually very much come from the clinical team in case if they're getting recurrent ulcers. You don't want to be like, I was told to stop the treatment. Okay, Because sometimes patients actually really struggle to stop any forms of treatment, especially if they do have real Zollinger-Ellison syndrome. Anyway, this patient stopped the H2 blocker and had the repeat gastrin, and it's still elevated at 197 picomoles per liter. So what should we do now? Who's going to do a secretin test? No one. Who's going to do an endoscopy? CT? Repeat gastrin assay? Mariana, what are you going to do? Your DD. Put you on the spot. Yeah, it's still elevated. This time it's 260. Yeah, you can do that. Or you could just go straight to an endoscopy. Yeah. Okay, so there's no right, no wrong, really. But at the end of the day, I've got a patient with GI symptoms, with a raised gastrin, and you want to work out whether this is actually due to gastrinoma, or is it due to what we call secondary hypergastrinemia, yeah, due to atrophic gastritis. So type 1 or type 2 gastric net, okay? But, you know, this patient had basically lots of polyps consistent with gastric net, but we checked for the gastric juice pH, it was high, it's around 6. So the patient has now a diagnosis of autoimmune atrophic gastritis. It's quite a benign condition. And essentially what we tend to do with these patients is just they have annual surveillance to start off with, and then over time we may extend. The gastroenterologist tends to look after the patients, but they can be at risk of also B12 deficiency due to the malabsorption that can occur, and we think about other autoimmune associated causes as well. But you can definitely withdraw treatments from them. They do not need the PPIs or the H2 antagonists. Okay. And in gastrinomas, patients with Zollinger-Ellison syndrome, they tend to be sicker, and they tend to have multiple ulcers as well, and obviously a low pH. So I hope I've highlighted the importance, you know, to establish the context in which gastrin test is done, and what are the two important conditions that you need to differentiate when you get called about the high gastrin results. Okay. Any questions before we move to the next bit? Okay. So I'm going to just touch on very briefly some of the other functional conditions. They are rare, and if we do, you know, get called about possible cases, you know, we're always accessible to advice. I mean, in the last 20 years, I would say I've only seen one lipoma case, so it is rare. But patients can present with very severe diarrhea, hypokalemia, achorhydria, and a hypokalemic acidosis. They're quite sick often by the time it's diagnosed. It's something that we pick up late, actually, and at the end of the day, treatment is to remove the lipoma if you can localize it. If not, you know, we consider variety of treatment, including ultra-tight treatment or steroids. But the VIT levels are very high, and when you do a gut hormone profile, you may get variable increases in chromogranin A, B, etc., depending. Okay, but VIT would be the main test that you'd be looking for. And glucagonoma is rare, but I must say I've seen quite a few glucagonoma in my time. And, you know, patients used to present, I would say, with these classic rash, necrolytic erythema migrans, typical exam question, mucosal abnormalities, stomatitis, glossitis, etc., potentially diabetes, thrombosis. The treatment would be to resect tumor. We give them zinc and a high protein diet because glucagon stimulates the catabolism of amino acids. So let's run through this case. He's actually a patient that's still on follow-up with us, 43-year-old. had a history of hyperparathyroidism at the age of 33, and then had surgery, had 3 glands removed, actually ended up with MEN1. And as part of the surveillance, we found that he had a raised glucagon, but no diabetes, no rash. Yeah. So very typical. Most of our MEN1 patients, if they get surveyed for pancreatic lesions, parathyroid, and then pituitary tumors. Even though the pancreas, often if you do imaging, you don't see anything, over time you will see something. And if you took out their pancreas, you will see small tumors. Okay. So this patient, you know, had several lesions, but also had evidence of a raised glucagon level. So we went on to do a gallium dotatate scan, and you can see here it shows this lesion in the head of the pancreas. He then had whipples, and one of the tumors stained for glucagon, another for insulin. And he was actually not too unwell. So it shows that actually, you know, we are picking up tumors earlier before they develop all those classic textbook pictures that we would see previously. Okay, but the glucagon in this context, blood level is very useful. So, you know, post-op glucagon level normalized. Everything was good, but then around, you know, 6 years later, his HbA1c started going up, and this time the glucagon's rising as well. We also looked at the amino acids, which was in general normal, and we then did further imaging, and essentially he had evidence of a recurrence, this time at the tail of the pancreas. So he's ended up actually, you know, with further surgery. Anyway, just to conclude this part, so, you know, gluconomas very often found incidentally on CT or during screening for MEN1, occasionally diagnosed on gut hormone screening. I mean, certainly when in these patients with the syndromes, we do follow them up, and when something goes up, we would, you know, whether it's somatostatin or glucagon, we then go on and look. But if we're randomly doing a gut hormone profile on someone with some non-specific symptoms, that patient, and we've seen a lot of this happen, ends up with loads of investigations, and we never find anything because the pretest probability was low already. Okay, so always bear that in mind. Right. Just to quickly also mention, we do sometimes see somatostatinomas. I've only ever seen one somatostatinomas, but you know, they can be pancreatic or duodenal, present with cholelithiasis, diabetes, steatorrhea. Pipiomas are really rare, often asymptomatic, presents with mass effect. And you do sometimes also see non-specific elevation in the PP level as part of your surveillance screen with your gut hormone profiles. And this is due to islet hyperplasia in the surrounding normal pancreas, or incorporation of isolated PP secreting cells within the neuroendocrine tumors. Okay, but it's often actually the PP doesn't do much, although we know if we give enough PP, we can suppress appetite. Then finally, I just want to mention other biomarkers for functional NET syndrome, because it's not just all about gut hormone. Gut hormones are useful, but we also have other markers, things like ACTH for ectopic ACTH Cushing's syndrome, for neuroendocrine tumors, PTH-related peptide for non-PTH dependent hypercalcemia, growth hormone releasing hormone, acromegaly without adenomas, arginine vasopressin for syndromes of inappropriate antidiuresis, calcitonin presenting diarrhea, flushing without MTC, insulin-like growth factor 2 for hypoinsulinemic hypoglycemia. These are rare, yeah? And I'm going to end with another case. Okay, most of you probably will guess this one. 52-year-old, history of loose stool, local gastroenterologist queried a NET, did a gut hormone, in 1993. That was the result. They searched and searched, they couldn't find anything. So we kept testing, and the test is sometimes up, sometimes down. But in general, the profiles are all elevated. What do you think is happening here? No, not in this case, but important thing to think about. Any other thoughts? I've not subjected these guys to neck clinics enough. Okay, so what should we do? Okay, I'm going to jump straight. We actually took a history. This person has lots of rabbits at home, and our antibodies is obviously from rabbit. So we added non-immune rabbit serum to the sample and repeated for gastrin, and everything normalized. So heterophil antibodies, a very fairly uncommon problem, but we do see this within our lab because we still use a very old-fashioned radioimmunoassays called our gut hormone profiles. And yeah, so taking a history, you know, on results that don't make sense, because this patient, you know, had, you know, all the results were all elevated, but then he was not that unwell. And then over the years, sometimes some went up, some went down, etc. So start thinking about some sort of interference if you do see this. Okay. So just to round things off, neuroendocrine tumors are diagnosed with histopathology, imaging, and also biomarkers. But really important that we don't try to first line diagnose with, you know, just a biomarker. Okay. The general biomarkers we talked about, 5-HIE, chromogranules, and CAR. Gut hormones are used as specific biomarkers for functional nets, and include insulin, gastrin, glucagon, somatostatin. These markers are can be used for diagnosis in the right context, useful for prognosis and localization. Okay, but beware of the pitfalls. Yeah, things like heterophil antibodies and other pre-analytical factors such as PPI, which can increase your gastrin. Okay, so this is just a very quick overview. Any questions?
How often the question can be, oh, I've got the sample, the data left around 3 hours of temperature, and still work, then how unstable are they?
So stability, I would say, is pretty important actually. But if it's still elevated, then you know you can. But I would say if it's been left in room temperature from anything in 2 to 4 hours, repeat it. Because especially if it's a patient that's been followed up or as part of ongoing treatment, you may still see a slightly raised gut hormone profile, but then it'll probably be lower than expected.
Slightly different RNA assays. So does that mean we effectively have, you know, different diamonds depending on the geography and where your samples go, or do you feel like
I think it would be, and if done in the right context, we sometimes, you know, get so because it's the diagnostic performance when looked at, it's not been reviewed, you know, in recent times, but when we previously looked at it, you know, it's quite similar between the groups. But sometimes when the test is done in the wrong context, we do get, you know, referral of cases where this patient's been investigated for the last 6 years for raised chromogranulin. We've looked everywhere, and the poor patient's been subjected to loads of imaging. Then we do a different assay, and it's normal. So you can consider doing that. That's the other option. You know, if it always comes down to was the test done in the right context. Yeah, you can, but then I would say, you know, it would not be my first approach to trying to diagnose a neck?
Natalie online just asking, can you repeat the stability criteria? They didn't quite catch the answer on the.
For gut hormones,
The gut hormone.
you
yeah.
need to collect it. It needs to go straight on ice, centrifuge, and then stored and then transferred. Any other, options, I can't guarantee the stability.
Great. Oh, and do you think there's a role for serum 5-HIA in monitoring?
Oh, it'd be
medication?
amazing. Yeah, I think the role-free team's developing a LCMS method. I'm not sure. Is anyone from the role-free here? Not sure how that's progressed. Would be great if you could have, a serum marker. It's just like how plasma metanephrines have moved away from, urine metanephrine. So it's so much easier for patients. But I suspect, there will be need verifications. Okay.